Alright, so hello and welcome. Howdy. We're going to take a look at another LeetCode problem, dungeon game. I'll get that going shortly. And let's see. Yes. Yep. So let's do that. Let's get right into it. I think I don't have anything incriminating here. Hopefully not. Yeah, okay. Alright, dungeon game. Let's get it going. 35%. Okay, let's see how this goes. The demons had captured the princess and imprisoned her in the bottom right corner of a dungeon. The dungeon consists of n by n rooms laid out in a 2D grid. Our valiant knight was initially positioned in the top left room and must fight his way through dungeon to rescue the princess. Okay. The knight has an initial health point represented. Wow, it's quite the problem. Has an initial health point represented by a positive integer. If at any point his health drops to 0 or below, he dies immediately. Okay. Some of the rooms are guarded by demons, represented by negative integers. So the knight loses health upon entering these rooms. Other rooms are either empty, represented as 0, or contain magic orbs that increase the knight's health, represented by positive integers. Okay. To reach the princess as quickly as possible, this knight decides to move only rightward or downward in each step. Turn the knight's minimum initial health so that he can rescue the princess. Know that any room can contain threats or power-ups. Even the first room the knight enters, and the bottom right room where the princess is imprisoned. Any room can contain threats or power-ups, even the first room the knight enters, and the bottom right room where the princess is imprisoned. See, the minimum health required. Let's check the constraints. Size of the dungeon is bounded by m and n by 200. Okay, so the dungeon is, and we don't really care what the initial health is. Doesn't even say what the initial health is. Oh, I'm sorry. I take it back. We need to calculate the initial health. So yeah, this is kind of a classic problem. This is probably a DP question. You could use memoized recursion, but DP is what we're going to go for. But basically, this is the sort of minimum weighted path to. Sorry, the negative numbers mean. Let me see. So it says C7. Hold on a second. -2 -1. Okay, so you need to. Okay, so alright, got it. So you need to have at least 1 health when you get to the last room, right? If you die in that room, it doesn't count. So this is of all the paths that you could possibly take from top left to bottom right, you need to take the path that requires the least amount of health. This is very similar to like sequence related questions where like you're looking for a subsequence. I guess it's like the minimum sum subsequence, something like that. Yes, definitely like a DP question. How would you do it? Top left, bottom right. So every position you're in, you have a choice between going to the bottom or going to the right, and you'd want to take the. Now, what's interesting is that if you just added the numbers together, -5 plus 3 is -2, plus 1 is -1, minus 5 is -6. So you actually want the largest number, believe it or not. Yeah, so the amount of health you need, if of all the possible paths you could take, the largest number that'll get you to the bottom. The reason why it's larger, it's actually presumably they're all going to be negative numbers, and negative numbers, like absolute value of a negative number, the further you go to the left down on the number line, those are actually technically smaller numbers. So smaller negative numbers means you would require more health to sustain. Larger negative numbers, which is confusing because they're negative numbers, but large, so you're actually looking for the largest sum. That's really it. You're looking for just the largest sum from left to right of all possible paths. And I think you can do, certainly you can memorize this in quadratic time and quadratic space, but you probably could do this in, you probably could do this in linear space, I think, quadratic time complexity and linear space. The linear space actually would be like a diagonal, a moving diagonal. So all the choices you can make from the first spot, right and down, and then from those options you have another right and down, right, the next diagonal, and actually you probably would go right to left on the diagonal. So initially you'd have -5, and then up and down you could do -4 or 24, and then here and here you can do oh, actually that's incorrect, this approach that I'm describing, because it's not the maximum path. It's actually on each path. Okay, that's tricky. So oh wow, that's subtle. All right. At any given, it's actually any given subsequence, subsum of that path. That's actually the value you want to use. So the problem is if you go left to right, like if you go down this way, at the end you'll have -7 plus 40 is 33 is 30. Hold on. 40 minus 10 is 30 minus 2 is 28, right? So actually this path would get you the most health, but the problem is that you need at least 8 health to get through this subsum. So it's actually the path with the, excuse me, it's the this actually, by the way, I think this is related to the there was an optimal path question. No, actually, never mind. I don't think it's related to that. Never mind. Maybe not. So actually, what you're looking for is there's really 2 numbers, which is like the subsum, I suppose, but also the path that you would take. You're trying to keep the largest numbers on the path at every point on the path. So that's interesting. So -2 to -7 gives you -7, -2 to -5 gives you -5. This is the largest so far. If you go to -15 and you go to -17, right? -15 here. Then here you go from -5 to 2. And then 2 to 3. It's also, you only really care about maximizing when you're dealing with yeah, that's really interesting. I don't know. To get all the way through, so you get -5, it's got to be at least 6, then it goes to 2, then it goes to 3, then it goes back to -6, so you need 7. Right, -5, so you 6 to get through here. That would put you, if you had 6, that would put you at 4, 5, and then this puts you at 0, so you need 1 more. Is that right? -5, -2, -1, -6. So yeah, you would need at least 7 then. Yeah, so it's actually going to be one less than the largest. So you only really care about the negative numbers. The positive numbers you don't really care about. How much health you would need. Yeah, because you could have like a totally positive path all the way through, and then you could just have 1 health, at least 1. Just thinking about this problem here. How are we doing on time? 9 minutes, 10 minutes, okay. Yeah, because if you just said give me the maximum, like the sequence all the way through, the maximum value, sorry, you get the smallest value throughout the sequence, is Smallest value throughout the sequence is going to give you what the cost of that path is, and it's sort of the smallest of any of these subsequences. But it's also like there's also a running total that you have, so you could store like two pieces of information, like a tuple of like what the current worst cost is at any given point, and then what the total is, best total, best path. I guess you'd want to at any given point you want the most health, so you'd want to maximize the number itself, but you'd also want to minimize. You could also calculate as you go what the worst cost for that path is, and compute that way. So you could do two values simultaneously. Yeah, I mean you could do that. That worst cost is just the minimum number that you see on that path. I guess one question though is like, okay, like let's say we computed from here and from here what the like recursive functions would give us, right? So from -5 you have, as long as you have 6, right, or at least -5 is the number. As long as you have -5, you can get down there from here. That's probably optimal. And the total amount is 40 minus 30 is 30. 30 and negative 30 and -5. And then over here, it's probably -3 to get in, and then you get 0, 1, -4. So the total sum is -8. Well, yeah, at any point it's -3, 0, 1, and then -4. So you need at least the worst number is -4, and the total is actually -4. So you get the same thing. So you get -4 and -4. What's interesting though is that this is -4 and this is -5. And so it's actually, once you look here with -3, you actually want to minimize the rightmost value. The leftmost value, you need to keep track of that only to compute the rightmost value, right? You would actually select the better rightmost value of the two, and so you'd actually select this one, this path, right? Because -6 is better than -7. Huh. That's interesting. Yeah, okay. Yeah, I think you can still do this quadratic time, quadratic space, but can you do this in linear space? Well, you only need, to make this decision, you only need these two. And then to make these two decisions, you only need these three. And then to make these three decisions, you only need these two. So clearly you can do this in linear space as well. So we can DP. Exact same idea that we just had, but we're going to start with, we're going to have a tuple of integers. And so computing the next integer will take basically the better of the two options, if you have two options, so down and to the right, and then you're just going to update the value for that spot. The array itself, so we're going to use one array for this DP. It's actually going to be a diagonal, so we're going to say all the way across is how many? It's the largest. It's got to be the largest spot on the diagonal. We could actually rewrite this as like sort of an upwards, a triangle that you're moving up on. So No, not really. No, yeah, you do need to use a diagonal. It's kind of increasing and decreasing. Otherwise, it doesn't really make sense. Like, yeah. Can you maybe just do bottom up? I mean, that's a lot simpler to think about. So make all the decisions from this side to the. No, you can't do it that way. No, it doesn't make sense. Because yeah, that doesn't work. you need an array. I think that's basically diagonals. What would be the longest diagonal? Well, if it was a square, it's kind of like the square root, right? Excuse me. Actually, no. The diagonal itself is. It just needs to be the rightmost. This side, this right side. So if m is the number of rows and n is the number of columns, it just needs to be the number of rows. Yeah, actually that's fine. No, that's fine because the way this is set up on the diagonal, it's every diagonal is just one down and one to the left. So as long as you have the number of rows, then you can sort of spread those out over the diagonal. Part of the issue with that though is, so it's pretty much you only use one element, and then use two, then use three. So the number of elements you use in the diagonal will change as you progress, as you move. I'm just thinking, how do we do this? So total number of rows, starting from the right side, we have something all the way at the bottom, which we can make. I don't want to reverse things. Like we can make the bottom the first one, and then when you go to the right, now the bottom is still the first one, and the second one is going up, and then the next one, the third one, is going up from the second one. We could replace the second one with going up from the first one, or replace the first one with this next one here, and then what happens is then you start moving back. So the third one is still the last one, I guess, gets second to last again. First to rewrite second, and first we stop using, and then second rewrites the last, and the last gets rewritten again from this side. So the last one, so so you'd have I, and I minus 1 affects your next element, and that's how you can do it. And then actually, so you go from 0 to n at the end, or n minus 1, however you want to look at it. So you could do the rows, the number of rows as your array for your dynamic programming. The problem with that is you could do the rows. The problem with that is, what if the rows are really small compared to the columns, and what if the rows are really large compared to the columns? So if the rows are, so here's a case where they're equal, but what if the rows are really small compared to the columns? Well, then you're going to be performing the same routine I just described multiple times from right to left, where you're sort of overwriting that row array over and over until you get to the end. That's fine. That's not a big deal at all. I think one of the issues though is, like, how do you know you're gonna not write like the first element right to left anymore, right? Like once you get past this point, then you're sort of processing only like a small part of the, like it decreases how much of the array you're still going to be processing. That's a good question. I would say something like excuse me. Yeah, because you only process. You first, yeah, you process the. You do 1, 2, 3, and that gives you, that's the number of columns, right? And then once you've done and well, okay, let's say the number of, there's more. I'm wondering if I should just do this like ON squared and see if I can optimize it. I'm pretty sure the only way to optimize it is to use linear memory, and you have to do it this way, the way that I'm describing. I'm pretty sure it's the only way to do it. I don't think you can finagle it. But yeah, so or do something more clever so it's not like this. So you would first you'd process the number of rows, assuming the rows are less than or equal to the number of columns. Process the number of rows so that the array is filled, and then now you're going to, yeah, assuming the number of rows is less than the number of columns or less than or equal to. Then once you get to that point, then you're going to process the rest of the columns, and well, I guess the whole time you're just processing the number of columns. I mean, you could process the whole array, the whole row or the whole column. Each time, it's just you won't have any values to copy, but at some point you stop updating. So we do the number of columns. Yeah, you actually need to do the columns and the rows each time. So columns and then rows, and actually the rows you do one less for the one less row. So it's kind of interesting. So first you do the number of columns from right to left, and then you do the number of rows from bottom to top. Well, excluding the last row, presumably. You don't need to do the last row. This is a little bit confusing. It's a little confusing. And that also tells you how far into the index you need to go to where, yeah, it'll modify the starting point into the index. So you kind of climb up this way. Yeah. You just exclude the last row for that one, I think. One more detail is that's if the number of rows is less than or equal to the number of columns. Let's say the number of rows is greater than the number of columns. What that means is you're not going to get all the way through the array, the column array, when you get to the rows. Yeah, so that's interesting. So I guess the size of the array is just going to be, it really is just going to be the minimum of the rows and the columns. The size of the array is kind of meaningless, somewhat malleable, somewhat meaningless. So what's going to happen is you get these three, you go up. Let's say if you had like a whole bunch of rows on top, you would go up to these three, right? Or yeah, you would get this diagonal, and then the diagonal will start moving upwards. And as you move upwards, you don't really change how much of the array you're modifying until you get to really towards the end. That's a little confusing. That's very confusing, actually. Yeah, this is extremely confusing. It's so much easier with a square rectangle. The rectangular array matrix, it's a little bit more involved. Yeah, so the array I think is just the minimum of the rows and columns, the array size, and I think you're just gonna have all zeros initially, so it's fine to. Part of the issue too is like, where are these values that you're modifying? Like you start off in the bottom right corner, initialize the first value with that, then the next values are going to be add to the first one the sort of next row or next column over to the left, and add the next row to the right. But I guess what I'm trying to say is that you have to keep track of a tuple, but you also want to know, like, where are these values that you're referencing, right? I guess in the tuple you'd also keep track of values I and j, so you know which part of the like what your position is in the matrix, so that way when you look up the next value, you know where to go. See, that's the thing, is I'm wondering if like you even need to do that. Like we can loop from the end and loop each position in the array is offset by some amount. Yes, that's so confusing. So confusing. You're actually going to operate over the diagonal itself, right? So you have a diagonal, you have a starting point for the diagonal. That's what you're going to update each time with the start of your loop. And you're going to say, like, the first index of the diagonal is going to be associated with the first element of the array. Second is the second element. Let me think about this. So as you loop over your array, you're looping through the diagonal. Updating the array appropriately. And the beginning of your diagonal is so that's going to make an L shape. Yeah, I guess that's kind of the deal, is that you could put this in sort of one loop that loops over the starting points of the diagonals, and then you process each diagonal in the array appropriately. The tricky thing here is that you have to handle this looping up the sort of L shape correctly, because once you get to the it's so confusing. Oh man. Once you get to the how are we doing on time? Yeah, it's gonna take us a while. This is not something I've practiced very much. This is gonna take a while. I've seen it multiple times, but every time it's like challenging. As you climb the wall, so to speak, even though you're starting the diagonal, you're also now starting at a different point in the array too. See, that's the tricky thing, right? You see how there's only two elements here. These are going to be the back two elements of the array, and this is the back one element, single element of the array. You no longer start at the beginning of the array. The problem with that, though, is this only matters for when you're starting to decrease the array that you're working with. In other words, if the array was the column size, the array size is the column size, then this is only when you get to the last column, and now you're going to start processing the diagonals on the row side. So when you transition to the next loop, so to speak. So you break this into two loops, right? Processing right to left until your diagonal is full, or at least the columns are the number of columns are processed, and then if that's actually it would be until the number of columns have been processed. If we did it really until your array is filled, really is what it should be. Until your array is filled, that's when you transition. So because if we had more rows than columns, then we would still want to use three elements and go up, right? So we would do 3 over, and then now once the array is filled, we wouldn't start decreasing. We would actually just keep going all the way until we get to the last 3 elements of the rows, right? The last 3 rows, that's when we start to decrease. Yeah, that makes sense. So, but what if we had more columns, right? So we would still want to pick 3 for our array size, and actually we wouldn't start climbing then until we got to the last 3 columns, right? That's when we start processing the rows. So that's when that's when we switch to processing the rows, but also simultaneously that's when we start to modify our loop slightly. So there's actually like 3 pieces to this, right? That's the key. There's like 3 pieces. The first piece is we're going to take our array, it's going to be the smaller of the 2 sides, and we're going to begin, we're going to fill the whole array starting at this diagonal point that we move right to left from the bottom row. So we traverse right to left on the bottom rows of the diagonal point. And as long as we can get through the matrix, right, to the end, we're going to, or as long as we're still in bounds, that diagonal, we're going to process our array, right? So we took the minimum. And then what's going to happen is if, so there's 2 cases, right? This could be, let's say it's a very large number of columns, so it extends way to the left. In that case, we have another loop where we would continue looping over the whole diagonal, the whole array. Excuse me. Still moving down the row, the bottom row, at the beginning of the diagonal, until we reached the. Actually, it would be, since the row is the larger piece, until we reach the last 3 rows, and then we would have a loop going up. Until we reach the last 3 columns, then we would switch and move up the. In fact, actually, that's not true. We would go all the way on the diagonal, all the way to the until we finish the rows. Finish the columns, and then we would start climbing the rows, and that would slightly modify where the beginning of the diagonal is, and it would also modify which element we start operating on in our array, right? So as we move up the side, we're going to sort of shorten our array smaller and smaller, so it only affects a smaller portion of the diagonal or of that array. That's if we have way more columns than rows. If we have way more rows than columns, then we do a similar thing where we actually, the size of our array is going to be still the smaller of the two, so 3 columns, and we're still going to process first the rows left to right, and then when we climb the wall, the difference here is that even though we processed all the rows, so in both cases we're going to process all the rows, right, and your diagonal is just going to kind of shoot off the end. Once that's done, when you're dealing with way more rows than columns, since the columns are, when you're dealing with way more, when you're dealing with way more columns than rows, the first case, way more columns than rows, then in that case, we made the number of rows the limiting factor for the array, and we can actually start to decrease. So we processed all of those rows. Now we can start to decrease the array as we climb on the columns. If we did it the other way around, where we made the limiting factor for the array the number of columns, so there's 3 columns and way more rows, and we're going to go left and then up, we actually are not going to decrease until we get to the last few elements of the till we get to the last few elements of the rows, the last few rows. So this is kind of interesting. We would process the columns, switch to rows, process the rows, and the last few rows, that's when we start modifying. Yeah, so actually the last few rows, when you switch the rows, the last few rows, so there could be 3 loops. One loop is for the columns, right to left. Second loop is if there are any rows extra, in other words, if this is row heavy, then you process all those rows as you normally would, right? Moving up the side of the row of the first column. That's the second loop. And the third loop is going to be the same in both cases. So in the first case, the second loop would be basically empty, like you would just immediately jump from through the second loop. But the third loop is always going to be there too. That's when you start to modify what the starting point of your diagonal array is going to be, and that's also going to just always be the last rows that are equal to the columns. So that's how you would handle both scenarios, and in all cases, what defines like how far the diagonal is going to go is it'll stop at the end of the array, or stop earlier if both. It'll stop at the end of the array. It'll stop earlier if both. Like, actually, the diagonal itself, like the position that you're processing, like at some point it will go out of bounds, and if it's out of bounds, then you just stop there. Yeah. So interesting. Yeah, actually, the size of the diagonal it just goes all the way until it's out of bounds of the matrix. So 3 loops to do this. Again, I've seen this not a million times. I've seen this multiple times, but I see it so infrequently that I don't really have it like down. But it's also kind of a tricky thing because obviously this is it's a DP question that normally I would use like memoized recursion, but you can use DP for these questions with the rectangles to optimize the solution. But yeah, you break it up into 3 loops. So the first loop handles and you're going to the size of the array is going to be the minimum of the rows and columns. First, you process the columns in the dynamic array, and then, or in the array, dynamically process the columns right to left in the array, and then, and that's the diagonal in the matrix. So you're sort of moving down the bottom row of the matrix for the beginning of the diagonal. Then you process, if there's a difference, if there's a excess of rows, you process those. In a second loop, you process that excess of rows, doing kind of the same routine. And then finally, once you get to the last few rows, which should be the equivalent size of the array, that minimizing amount, that's when you start climbing up the, or once you reach the, also the second loop would exit. There would be, I'm sorry, there's more like 4 loops. So first loop goes right to left on the columns. Or on the columns. If you have an excess of columns, then you're just going to keep going all the way to the limiting factor. Keep going. If there's an excess of rows, if there's not an excess of columns, if there's an excess of rows, it just goes all the way down until you start the last few. It actually goes all the way down. I'm sorry. You go all the way down until you start the rows. If there is an excess of rows, that's the same deal. You go all the way down until you reach the columns, and then there's going to be a second loop, which is if there's an excess of rows, you process that excess of rows. If there's not an excess of rows, then you would skip this. So if there's an excess of columns and not an excess of rows, you'd skip the second loop, start the third one. If there is an excess of rows, then you would do the next loop is basically the same as the first loop, except you're going to be moving up the diagonal, and you're going to stop at the last few rows. You're going to stop that loop where the last few rows are reserved. Those are the size of the diagonal array. Those last few rows you're going to process differently in the third loop. So if you have an excess of columns, you actually skip the second loop altogether, but if you have excess of rows, you perform the second loop. And then the last loop is going to process the size of your diagonal, that number of rows, and those rows we're going to continue going up the diagonal, or not the diagonal, up the left column, and actually you're going to each step you're going to move forward in your array, so the processing in the array is no longer to process the certain elements to the left of the array, or the beginning of the array, so they're not going to be processed anymore. And then at the end of that, you should have all the way in the last element of your array should be what we're looking for, the tuple we're looking for. So that's how we're going to loop through this. So it's sort of an L shape, looping through L shape across the diagonals. So we're going to use dynamic programming to do this, and we're going to use tuples. Also, the algorithm itself is just going to be so the elements at so if we had DP as our array, it's going to be when we process the diagonal, we're going to process sort of each element. It's going to update the first diagonal element will update the first DP element. That's as if we move to the left. The next diagonal element is going to update the DP element at that spot and the previous DP element. The way we're going to do it is it's the DP element. It's either going to be, and I guess we create a new diagonal each time as well, and just swap them. What you're going to do is you're going to take the either you move to the left or you move up. And so what you optimize for when you're choosing between left or up, it's going to be, So actually, the DP itself, it's going to be, you absolutely move to the left. The idea is actually going to be that it's you have the optimal solution from the position that you're in. So the first position must move to the left. The second position could come from. Now here's another question. Do we go? We update our diagonal. Actually, what is the algorithm exactly? Like I went through all this time, like just how we're going to traverse these diagonals. But actually, the question is like, let's say we have this first element, it's -5, -5. -5 is the total health at that point that you have, right? And the total summation, and then the other -5 is the minimum at any point, minimum health you have at any point. So getting there, the optimal minimum health. So it's the optimal health that you have, and then the optimal minimum health. So on the left side, we're going to update our DP to, we can add this number to DP1, to update DP1 to adding this number, or DP of 0, right? And I guess we could create another array and do it that way. I think it's simpler because we kind of need to reference back. We don't want to overwrite this. So that becomes 25 and -5 stays, right? And then the second element, and so this first one should be, basically we're making a decision on the next DP0. So that's going to be below, there's no element, it's out of bounds, and to the right. And below would be just DP -1, and then to the right would be DP of I. So DP of I -1 and DP of I, if they exist. And so we do, basically we take the element that we're going to consider when we consider these two selections is the second element. So that whichever one has the smaller element, we're going to take that element and then add this value to it, and also potentially update the second value as well. So there's like a little bit of logic involved there, but it's not too complicated. And that's going to be the new value for DP0. And then DP1 is same deal. It's going to be the previous DP1 compared to the previous DP1 for that spot compared to the element that came before that. So obviously there's only one element. So again, this is really just the previous element, and that's it for both of these. Those are the only two choices. So you have DP0 and -1, and then this is +1 doesn't exist, but the +1 doesn't exist, but the -1 does. So it's just DP0 compared to. So both of these would end up with, this is 25 -5, and this is -4 -5, right? And then same deal again, and then you would swap these two, set up, make this the previous array, and then delete, not delete, but don't worry about this array. So then now you update again. You say take the previous array, so there's no DP -1, but there's a DP0 to compare to. Add 10, we said that was 25, so add 10 is 35, and update -5 and 35 is still -5. That gives you the next DP0. DP1, same deal. You have two now to look at, DP0 and DP1. So now you can say from 25 you can subtract 10, you get -15, or excuse me, you get 15, but 15, you still have 15 -5. And on this side you can say, well actually you want to pick the one that has the best, what do they call that? The best minimum. So actually, if the best is minimum is both, if both of them are equal, I didn't think about that. If it's both -5, then you pick the one that has the larger health. So this one would actually go to 30, and then you'd update appropriately. So this is what we said is negative. We said it's 25. Now it's -15 with -5, and we would ignore this other one here. And then finally here, there's only one option. So, but it would be dp of, so this, it would try to go to the right basically, but there is no dp, there's no diagonal there on the right, and then you could also, you'd be stuck with only the one on the left. I think part of that issue is like, we have to handle that correctly, right? If one of these is out of bounds, to automatically switch to the other one. How do we handle that? Could use a series of if statements. So just like, if A is out of bounds and B is not, then pick B. If B is out of bounds and A is not, pick A. And if they're not both out of bounds, then do a comparison to pick one. And so you could use like the choice could be a pointer, like a const pointer that ends up being pointed to whichever one is the winner. And then you could just modify the, you could set a like a reference to whatever that const pointer was pointing to at the end of that logic. I think that's fine. I think that works. It's a little bit involved, but I think we've done something similar to that before. Just like to handle that sort of in C++, handle that in a way that's like not really awkward, because you want to handle that logic correctly and just set some pointer to whatever your decision ultimately ends up being, but you do want to handle those cases correctly. And then, right, the processing is going to be whichever one you choose, which is going to be, so the choice is first compare the minimums you've seen so far, like you want the smallest minimum, or no, sorry, you want the largest minimum, and then you're going to compare. So you get the first compare on the largest minimum, and then second compare on the largest. First the largest minimum, and then it's the largest health value, right? So in this case, the minimum we said was -5, and then here you end up with health of I think -1 and -5 over here. So -1, -5, and here is what did we say this was? This was 15 and -5. Now this is really interesting. I think maybe I'm doing it wrong. I think maybe we do need to actually go left to right or something, or we need to do this a different approach, because I'm going to get the wrong answer if we DP this way. So, because when we look at this one, we get -1 and -1 and -5, or yeah, -1 and -5, and this is 15 and -5. So we'd end up picking 15 and -5. We'd end up with 12 and -5 here, which is actually, it's incorrect, I guess, because we're this actually requires a lot more health to go this way. So I think part of the issue is we're going backwards. So I actually think we need to reverse our health totals or something. I don't know. That's tricky, because part of the issue here is you want to know what the health totals are going forwards, and what those minimums are going forwards, not going backwards. Yeah, because the problem there is if you have a large piece of health that you pick up, then it looks like you don't need as much health to get through here, and that's kind of awkward. That's a little bit awkward. So maybe we do go the other direction. I'm not really sure though, because if we go the other direction, then yeah, we can update our diagonal in a similar way. It's almost the same algorithm, but our first diagonal would be -2, -2, and then our next diagonal would be -7, -7, and but we're actually, in this case, we're actually going up and to the left then for our numbers. So -7, -7, -5, -5. This one ends up being 3 and -7. And then this is -5, -5, -15, -15, and -2 and -3, I think. Yeah, actually that's much better. So we would start off, diagonal extends here, diagonal extends here, diagonal gets smaller here, and then diagonal gets, so how do we do this? We would say, it's similar, we just go left to left, down and to the right instead of right, left and up, down to the right. And down and to the right instead of left and up. And we also want one other piece, which is does this, so before the way we did it was we were extending the diagonal and then bringing the beginning of the diagonal here. So the beginning of the diagonal is actually going to stay in the same kind of spot. So this will be the first element, then becomes related to the previous first element or the previous second element. So as I and I plus 1, modifies I, potentially updates I. So yeah, you just look at I and I plus 1, that's fine. And there's no I here. There is an I plus 1. Is that right? That seems weird. That doesn't seem right. You're going to the left and up, right? So what would be left and up? It would be on these diagonals, left is I and up is I plus 1. Yeah, it's I and I plus 1. So this is left is I, which so when we create a diagonal this way, there's an I plus 1. So I guess, so this actually has to start at the back of the diagonal. That's, I think, the issue. This will start at the back of the diagonal, and then we'll slowly, as we move down, we'll move closer to the beginning of the diagonal, because there won't be, there's an I plus 1, but there's no I there. It's just empty. Yeah, so that's a little confusing. When we go backwards, when we go down and to the right, I guess we don't have to do it that way. We could do, the reason why you'd want to do it that way though is that you want to be consistent, where your I and I plus 1 comparisons here are like you don't want to just suddenly make the beginning of the diagonal always I, and so this is comparing I and I plus 1 is like all the way up here on this other diagonal, right? Like that doesn't really make sense. You want other previous I value to be the left at all times. And so in order to enable that, you want to actually shift you grow your values from the right side of the diagonal down to the left side. Little confusing, I realize. There's also a few ways to do this, so it's not obvious like what I'm referring to if people are lost. How are we doing? We have, yeah, it took us an hour to kind of work our way through this, but actually we did it wrong the first time. It can't go from right to the beginning. It's got to go from the left down to the right side. Same idea, same algorithm. It's just slightly different. So going left to right, we're going to start at the back of the array is the initial value, first value. The diagonal is going to, in that case, we can say, so it's going to be the start at the back of the array, but we can actually start by saying we're still going to go left to right on the diagonal, but we're going to start in the array at sort of a beginning point. So because we're going to go the other direction now, we're going to first find what the limiting factor is. So it's either the rows or the columns. Let's say if we're row heavy, that means the columns are the limiting factor. We process one loop for that limiting factor initially. Then we enter another loop, which is the excess of rows. I'm sorry, if we're row heavy. If we're row heavy, process the excess of rows, which is going to keep our kind of, we're going to process the rest of the rows after that. And we're going to just loop upwards on the diagonal each time, as described previously. And then we're going to get to the bottom of finish the excess row loop, and then process the columns. So that's going to be the same kind of idea we were just describing, where actually the limiting factor is like whether diagonals go off the edge. So that'll automatically limit itself, so we don't actually need to think about it too much. Yeah, so that'll work if there is not an excess of rows. That second loop we won't enter. If we have excess of columns, so we'll process. So we said we're going to process the columns first, that limiting factor first, which will process all the rows, right? In that case, the rows are the limiting factor. Process the rows. Then it switches to columns, processes all the columns, and again, the columns portion will automatically kind of limit itself the way the diagonals are set up. So yeah, so it's still the same loop. It's just the first, second, and third. The third and the first loop kind of get swapped, more or less. And now we're also processing the diagonal slightly differently. So that should work. Let's try to see if we can code this. If we have the right idea. So first we have a vector. So this is a really interesting question, and it's very similar to other kind of grid-based questions that are on LeetCode. There are a few. This, I think you can do this really quite fast. We're actually going to call this grid instead of dungeon. Yeah, and we're going to use, really don't need much. So const, we're going to call this like min factor, min f is going to be, so we could do const and rows is going to be grid.size, and these are ints, and then columns is grid of 0.size, and we also want to know some other things. It says that there always will be at least one row and one column. Okay, so that's good. So we can just use this outright. We don't need to check for like sort of pathological conditions. So min f is going to be the minimum of the number of rows and the number of columns. right? So one of these is going to be smaller than the other. We're going to have two loops. So we're also going to have int d, we'll call it, or actually we say dp, and the size is going to be the minf. We're going to have, so process, and we could just set this initial value. Start off at 0, so we'll just initialize all of these to 0. So process initial rows. So there's going to be an extra variable here to make sure that we start off at the back. So int, I don't know, we'll call this x. I'm not sure what to call it. It's not like a buffer, it's like a starting point, like position we can call it. Maybe position is fine. So the position is going to start off at min f minus 1. And also we're going to say row r. It starts off at the top row. And we're going to say row is less than the number of rows, and increment r. So we're going to process every row up to, so it's actually going to be the min f rows. That's how many rows. So yeah, we're going to process min f number of rows, process the initial rows, and minimizing factor. And we have this position. So now we're going to say d int d, or diagonal. And so we're actually going to have, so we're going to have r and c is always 0. It's actually going to be, yeah, so this is kind of interesting. So int, so it's going to be int c equals 0. R is less than, well, really it's just C. I mean, R we know is not going to go off the bound, but C might. So which row? Or so let's say row. Let's do row. This is a little confusing how this is going to work, but this is how we're going to handle processing the diagonals. So process diagonal. So the way it works is we have R and C. So R is going to start off at the row, and C is going to start off at 0. And we're going to have, as long as R is less than the number of columns, and C is less than the number of rows, or sorry, excuse me, R is the number of rows, which it always will be, I think. And C is the number of columns. And you're going to increment the row and increment the column. Okay, that's really confusing, but yeah. No, you're going to decrement the row. Sorry, decrement the row. Row is greater than or equal to 0. And increment the columns. So moving over one column to the right and going up one row. That's going to put you on diagonals going upwards. And we'll say, now we're saying we have to have that logic where we choose. So and there's another variable d, which starts off at 0, and d increments each time as well. So that's the oh no, whoa. What happened? What did we do? Ah, I don't want this. I'm blind as a bat, so it's hard for me sometimes. D. Okay. All right. Yes. So increase the. Now also there's another piece here, which is what I was saying. This position. This D actually starts off at position, right? And then it goes upwards. So yeah. That's also tricky. That's the part that's really tricky here, because we're actually going to start at the end of the array, and we're going to, as we go down, we're going to add more elements to the array to consider. So now we want to select, choose a pointer to one of these two possible choices for our array. So we're going to update our value in this diagonal value, considering the left value and the value above in the previous diagonal. So we're going to have a DP. We're going to have a previous. So it's not really DP anymore. It's, well, DP, and then we could have, you could say, previous is probably better than DP, right? I like previous better. Previous makes sense. And then there's another one that's, it's not the previous, but it's going to be the temp, sort of a temp array. So you're going to write to the temp array and then update the previous to what the temp is, and do it that way, which is kind of interesting. And both of these could be just made empty. Okay, and then previous of, this is min f minus 1, that is going to be set. Now these are actually not just ints, these are tuples. So that was the thing we were getting at before. These are special. This is standard make tuple of 2 integers. It's going to be grid of 0, 0, 0, 0. So the initial value. Excuse me. So the way this works is, and boy, we spent a lot of time on this. Right, the way this works is the last element of the array in the very beginning is going to be set to just the first element. So process diagonal, what we say is so there's going to be no left and no right, no left and no up on this part. Yeah, that's kind of interesting. The initial value, it doesn't get updated or modified on the first row, because D is position, and then we would say R is 0, C is less than the number of columns. That actually works, but then when you try to process above and below, yeah, it's a little confusing. I don't know. This first one's kind of redundant. But you would say, so we want so there's D and D plus 1. We want a pointer to a tuple. We can do that. That's fine. So const standard tuple pointer selection, or st, call it t, and we'll just set that to a null pointer for now. We're going to say if, so there's a few conditions here. If d minus 1 is less than 0 and d plus 1 is greater than or equal to 0, right, so if it's actually d and d plus 1. So d is never going to be less than 0 though. So that's really tricky. I think you've got to say d and d minus 1. D minus 1 is the left, and d is where you are. See, that's really confusing. This position is going to decrement each time, by the way. We want to modify we want a temp of d and temp of d plus 1. No, I want to modify temp of d, right, as we increment temp of d, and we're going to choose. So the first execution kind of doesn't make a lot of sense, but the second execution, if we sort of look at the second diagonal, that makes some sense. So d is going to be from 0, it's going to be 0 and 1. On 0, we're going to say the previous array doesn't have, so it's not going to be 0 and 1. It's going to be whatever d is, which starts off at position. It'll be position minus 1, and we check position minus 1 in the previous array, which, right, so the first position will always be excluded. That's the bound. So it's not less than 0. It's d and d plus 1, but it's d is greater than position plus 1. Yeah. So in all the other diagonals, it's going to be really this won't be an issue. This check, but basically past the first position we won't check. So if d is less than or equal to that position, right, because we decrement the position first. If we're equal to that position, we exclude the first one altogether. And we also need to have d is less than or equal to that position, and d needs to be in the right spot. D plus 1 is less than or equal to min f, or less than min f. That means we select t is to be pointed to the reference to which tuple. It's going to be previous of d plus 1. So we exclude the first array, first element, and include the second element. This is a similar thing if if it's not the case, so if D is greater than position, which it could be in some cases, and D plus 1 is greater than or equal to min F, then we set T equal to previous of D, right? Otherwise, we have two different tuples to consider. So if const auto AB is equal to previous of D, const auto CD is equal to, we shouldn't do that, we should do A1, B1, A, B, C, D, we could do A, B, C, D, E, F. Could we do E, F, H, I, J, K? We could do J, K maybe. A, B, and J, K. Now this is we're making a decision between each of these tuples. We're going to say if B is less than, so our check is going to be B is less than K, and so B is less than K, then we select or B equals K, and then we want to select, so if B is less than K, we said we want to pick the larger of the two. We pick the second one. If they're equal to each other, then check is going to tell us whether or not we're going to pick the second one. Actually, we do it the other way around. We could do the first one. So A is greater than K, or B is greater than K. If B is greater than K, if they're equal to each other, then we want to pick the larger health total, right? So we always want to get more health. So the larger health total is going to give us so we'll pick B is greater than K is what we want, or B is equal to K and A is greater than B and greater than J. So either larger health total. So we're going to prioritize first the larger like required health, or not required health, but the larger sort of how to express that, the larger secondary sequence of health totals. So the larger of the, it's not health required, but I want to say health required at any point, but that's kind of a misnomer to say that. It's the larger health at any given point. It's not, I don't know how to express that. It's the, so at any particular point, your health could drop lower. It's the larger of the lowest points of your health. Yeah, that's the larger of the lowest points of the health up to that, through that path. That's so confusing, but it's the larger of the lowest health through that path. Prioritize that, and then if they're equal, then prioritize the maximum health that you have at that point, right? So healthier is just always better if you have the choice. So now we say if check, then we can set T equal to previous of D, otherwise T equals previous D plus 1. So the key here is if you disqualify D, so you could disqualify the first one, and then you select the second one. If you disqualify the second one, then you select the first one. That's the idea. And you would really just say T is equal to you could use a ternary operator here. I think that makes sense. T, and otherwise we do previous D plus 1. Okay. So that's the prioritization, and now we can say const auto AB is going to be we can destructure the tuple that T is pointing to, and now we have the values that we're going to update. Temp of D2 is then standard tuple of, so it's going to be make tuple, and it's going to be something kind of specific. So it's going to be A plus, oh, no thank you. It's taking a really long time to code. It's going to be, so this is kind of interesting. So it's A plus the value at this particular point, which is R and C is grid of RC, right? So there's that value, grid RC. And we actually want const int new val, we'll say, is A plus grid of RC. Which could be a negative number, by the way. So new val. And then we're going to say this is the smaller of new val and B. So you might update this value here, right? With your new value, if you subtracted a whole bunch of health and you dropped all the way down, you're going to take the smaller of those two. So you update now. That gives you temp D. Okay. So this is going to be the loop we run pretty much everywhere, but this part of the code is the part that's like most involved. This part obviously is not too involved. So now process the initial rows. This is kind of heavy, how this is being done. I'm wondering if maybe we can rewrite this portion to be like a lambda expression of some kind, and then we can rewrite it, reuse it, but instead of like sort of duplicating code. It's a little bit different in each case. But so here, process initial rows. Now it's going to be process excess rows. And the row here, so we process the min f rows. Our position doesn't exist anymore. Now it's basically 0. Row is going to start off at min f now. And I think the key here is, yeah, we could say as long as the row is less than the number of rows. So if it's equal or, so min f, yeah, min f is never going to be more than the number of rows. In some cases it can be equal, in which case if we don't have excessive rows, then we would be done. Now what's interesting is, if we had an excessive number of columns, then we would be done. We don't enter this loop. Right. If we have an excessive number of rows, then we do enter this loop. And we just go until we're done with the loop, the rows. Right. Okay, fair enough. So row min f, increment the rows. Don't have a position to decrement anymore. Process our diagonal. This actually just starts off at 0 every time. Similar thing, R is greater than or equal to 0, C is less than the number of columns. This is oh, this is always gonna be greater than or equal to 0. This is actually, oh yeah, well we're decrementing the rows, right? Oh, I see the problem. Let me think here. Yeah, we're still decrementing the rows. This starts off at yes, yeah. So really, at this point, this is going to be bounded only by the columns. Decrement rows, increment columns, increment D. This is all the same. Just that D is going to start off at 0. D less than or equal to 0 now. Our D is greater than 0. So if D is 0, we throw out. There's no D minus 1 that we'll throw out. That we can throw out, and then min f. Yeah, this is actually the size of the diagonal itself, so that should be fine. Same kind of deal. I guess these are the same, except you could just set the position. You could make this a lambda expression. I think we probably should. I'll think about that. This is all the same code, same idea. This is all the same. Yeah, it's pretty much all the same. So I'm very tempted to make this a lambda expression. I'm going to do that. I'm actually going to go ahead and do that. So we're going to say const auto select equals the following routine. And we're going to have int position. Actually, it's probably better to inline this than I think about it. Like as a function, that's okay, I guess, but it's actually kind of costly to have a. I'm not gonna. Okay, we're not gonna do that just yet. We can later. I'm also assuming it's going to be correct when I write this. How are we doing? An hour and a half? Wow, it's taking really a lot of time to code. Okay. All right. So process excess rows, and finally process columns. And so now it's going to be a column is 0 initially. So we don't need to process the first column, do we? Processes all the rows. That's this one at the top. Excuse me. I don't know, man. This is there's one more issue here that we didn't think about yet, which is when you process the first, let's say, first 3 columns, first 3 iterations here, position. So you perform these 2. Position. So we have 3. Position is 2. We don't process anything the first time. Second time, the position is, this row is here. Position is, oh yeah, we have to also update previous and temp. We'll get back to that. But excuse me. So we should also. That's confusing. Oh, that's so confusing. Yeah. We don't set this initially, do we? Not really. This is very confusing. Okay, my brain's starting to hurt. Yeah, because we don't set the initial value as part of like the DP. So I think what we ought to do is we do set the initial value, but this won't work properly if you don't set the initial value, is what I'm trying to say. Another thing that's really confusing here too is what if these are, oh, there's so many questions that still haven't answered. What if these two are, what if these two values are, what if they're both positive on the right side? If B and K are both positive, in that case, you actually would want to pick the smaller of the two, but the one that has the larger health. Yeah, so this check would be interesting. So if B, so if B is greater than 0, K is greater than 0, I want to update check equal to, will be sort of reversed the priority. Not reversed, but A and J. You're going to compare A and J with priority then. And B and K later. Yeah, so that's kind of interesting. Yeah, you'd reverse the priority if both of them have positive health and the sort of the minimum health that you need, or the minimum health that you're going to lose, or if their minimum healths throughout the sequence are actually both positive numbers. It's so confusing the way I'm describing it. I was going to say like it's minimum damage or minimum health as a negative number. So it's minimum damage as a negative number. If both of those are minimum required health is a negative number. If those are positive, then that means you're actually going to gain health in both instances. So you'd want basically the most health you've gained up to that point. So you'd swap priorities. I don't know if this is going to work properly. You know, now I'm looking at it, and this is also one of the reasons why you probably would want to make this a lambda expression. If it's not correct, I'll switch it to a lambda expression. Yeah, that's. Oh no. That's another consideration that I missed. And also another consideration is, yeah, how many times do we, like when we transition from one loop to the next? So it seems clear to me that this loop works nicely with this one, right? Because we're not overlapping at all. But this loop when we process the diagonal, do we skip the first column processing? I think we do. I think we actually, we don't start off at exactly, so we'll start off at the first column to the right, I think. Yeah, so we can do column 1, and the row is always going to be number of rows minus 1. So we're gonna trace the bottom row, and we're just gonna say column is less than number of columns. Yeah, clearly, I mean, the way you'd say it is that, yeah, you're gonna process 1, 2, 3 row diagonals, and then you're gonna process 1, 2 diagonals, so 1 less than the number of columns. Row doesn't change, column does change. I did this wrong, didn't I? I did. And now we have process diagonal. R starts off at the row, C starts off at the column, D starts off at 0, R is greater than or equal to 0, C is less than the number of columns, and decrement R, increment C, increment D, and make our decision, our choices, as mentioned. Yeah, these you'll always be able to pick to the left and above in every case. I guess another thing to consider is the way we're doing this min-f. Yeah, so it makes a lot of sense in this case, but actually in the middle case here, actually every row should have. I think min-f still works because every row, yeah, you're always going to be able to go to the right, go above, go to the right, or yeah, above, which is d plus 1. Yeah, so actually it works out in all these cases. It's fine. Okay, so the last thing would be, so what we're missing here also is swapping. Oh yeah, there's 2 more questions. So swapping temp for previous and previous for temp. So once you're done processing diagonal, then you want to say swap previous with temp. So for int I equals 0, I is less than min-f, increment I. And we're going to say previous of I equals temp of I, and that's all we really care about. Or write to previous of temp. Or write previous of temp. Yeah, we do that at each case. And the other question is, do we need to make sure, because we're writing to temp from previous, the first iteration, we're going to overwrite here previous with temp, and if we don't write anything into temp in the first iteration, then we overwrite our first value here, and then we get nowhere in our algorithm. So the question would be, can we Oh, this is kind of interesting. This should actually crash. I'm not even thinking about it. Yeah, the first iteration, this is going to crash. There are multiple questions to worry about here. That's good. Excuse me. Mm-hmm. Um, have to qualify this part so we don't crash. Yeah. This all needs to be if t. So you won't write anything initially, and that should cause yeah, we could just make sure we write something. Maybe we could do that too. Yeah, we could do it this way. That works. Oh no. No, that doesn't work. Okay. Alrighty. Alright. Why not just make these copies of each other? I think that solves the problem, quite frankly. This is a little bit confusing, I realize. Yeah, this prevents the crash that's going to happen on the first iteration. And then so you have to actually kind of modify each of these with that. This part we can copy in here and copy in here. And we also can, not using a lambda expression. And we also have to have this else if here for position is 0 also. Oh, no, oh yeah, okay. Okay. And finally this part is just copy pasted. Yeah, because it's actually possible for T to not have a, not be pointing to anything, which could cause issues. And finally at the end we return, so we say const auto AB is going to be equal to previous of, is it the 0 or the last one? I think it's 0. And then we can say return, it's going to be -1 times b. It's going to be more like the following. So you always need at least 1 health, but you could take b, which is going to be some negative, potentially some negative number, negate it, -b plus 1. And so you have to have at least 1 health more than that. Something like this. What a piece of code. What a program. It took me 2 hours to do this. And I don't think it's... Oh, it's not correct. No! It's wicked fast, but it's wrong. Oh no. What happened? Wow. Oh, I see. That's wrong. I see. I think it's the maximum of these, actually, not minimum. It's got to be at least one, but yeah, okay, I think I did that wrong. Oh, there's so many test cases to go through here. I could write a Python script to generate some random test cases. We could do that. Let's do that. Let's do it. Let's programmatically generate some. I have a lot more confidence now in my ability to generate these test cases with a Python script. So, all right. Temp.py. I don't know what to name this. So we can use this. All right, let's do 10 cases. That's 10 should be fine. Okay, I guess we're gonna do it this way. 10 cases is fine. And we're gonna generate rows and columns. So num rows is gonna be rand range from 1 to 200. Num columns. We should call this R. We don't want to use, yeah. I realize R is kind of awkward. We can actually, you can import in a way where it doesn't have a name. I forget how you do that. I think it's import lib is what you say. So this would be, how do you do that? There's a way to do this, hold on. There's a way to import. Oh, maybe that's a built-in, actually. I was gonna say there's a way to run things. Hold on. Is it built-in somewhere? Where is the built-ins? Language reference, library reference, built-ins. Let's reload one of these built-ins. It's not. Yeah, there's a way to load a library such that it doesn't require you to call the function name, something like that. Can we do that? Hold on. Can we? Exit this for a moment here. Python import rand range 0 100. Isn't there a way to do this where we don't have to need to call the library name, like basically import into the names in the namespace, import the symbols? Actually, you can do, so we can reload random. Huh. Yeah, so that's a little weird. Import into namespace. I think that there's a special way to do this. I think it's import from is what you do. I forget how to do that. I think you can do something like the following. It's been a while, but you could do like from random import that. There we go. Now we say rand range 0, 100. Hey, there we go. That's what I want to do. Okay. No, it's really interesting. I think it's C++. Excuse me, Java. Java, you can do some strange things with your static imports, they're called. You can import, static import is similar to what I just did. You can import like just a function name or just a variable name, just a constant, I believe. Like, yeah, just a variable basically from a package. So let's go back to our temp Python script. Because I just don't want to just keep writing. I didn't want to name my library some like just random small number of characters. I didn't want to keep retyping the library name over and over. So I figured an import statement like that is fine. So rand range from 0 to 100, also rand range, or 1 to 200 rather. And then we're going to say for A in range of the number of rows, so each row we're going to generate. For B in the range of columns, we're going to have a returned ret is a list. We're going to say, could do this. You could do a list comprehension, so ret dot append. So actually, these both could be list comprehensions. So this is going to be for B in range, number of columns. We're going to generate rand range of row ruby with rand range of I think it's inclusive, and yeah, so, and then actually this doesn't need to be, you could do just for A in range. Could do this for each for A in range of number of rows. Whoa, there we go. Okay. So, is this correct in terms of like what we can do here? By the way, I was supposed to do. I was not supposed to open this the way that I opened it. I keep forgetting to do that. Because I have to go all the way, scroll all the way down to go to the next page, and then there's a way to revert back to the old style, which is a little bit easier for me to navigate. But anyway, so all right. Yeah. So we'll close this. Okay. I think this. Oh, yeah. I think it works. I mean, it might work. I don't know. Could just use Python's print feature. Oh no! Stop. All right, let's try this. See if this gives me errors on the test cases. If it even processes the test case, it gives invalid test cases. Are we wrong? Hey, we're correct. Oh, well, that's confident. That's good. Wow. Huh. No kidding. All right, let's crank it up a notch. Let's go with 100. Ha ha ha. So I think we're probably correct if this works out. This might take a moment. Oh, immediately. Okay. Try again. So that should be 100 test cases? Really? Is there really 100 test cases? I don't believe you. Okay, I believe you. Does seem like a lot. Oh, one of them is wrong. Wow. I'm never going to find it. The one that's wrong. Oh, I was going to say, I was like, 10 test cases is a high level of confidence, but there's a good chance I did something wrong, and it's very slight, very subtle. And I was thinking like, okay, let's try 100 test cases. Maybe we'll just happen to come across that one combination of things that I made a mistake on. Boom, we caught it. I thought that might happen. So this is what they call, excuse me, this has a name, what we're doing. This is a, what do they call it? This is fuzzing. It's called fuzzing when you try a whole bunch of different possibilities just to see if you break anything. Yeah, so we fuzzed our code here. All right, now let's look through 100 test cases to find the one that's wrong. 1. 812, 1, 1. What do we expect before 812? Oh, man. Oh, 6352. Oh, whoa. Oh. Excuse me. Well, how did that happen? Whoa, what happened there? That's a big difference. Which one's 812? How many is that? So it's somewhere, there's 812 here. We're going to open another one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So 35 from the bottom is the test case. By the way, these test cases are enormous, potentially. So, oh no. How am I even going to find this test case? Oh no. Maybe I can open it in Vim and see that I can help out. So, oh boy. Oh. Need a better way to label these. This is great. I guess I could read this line by line into another Python script. Just call it process.python. Maybe we can do this. You ready? Okay, I got an idea. Got an idea. All right, it's 35 from the bottom. So I don't know. We'll grab like a range of values. This is fun. All right, we're gonna do some terminal shenanigans here. So we're gonna Python terminal. We're gonna say from OS import everything. We're gonna say f equals open tt for reading. It's not defined. All right. OS print working directory. Current working directory. Nice. Get current working directory. Okay. Plus TT. F equals open. Okay. Oh. All right. Try again. Okay. What is How do we Python open? Come on. This is... drive me nuts. It's not, it's an integer, but how do we... Oh, what? Mode. What? How come I can't just use the, what? Come on, man. Oh, okay. Flags. Why though? Oh, please no. Ah, it's gonna drive me crazy. Oh, okay. I guess, all right. Confused. Yeah, confusing. Very confusing. So, why not, why do we need to set flags? Can we just do O read only? Why do we need flags? Ah. Yeah, how come we can't just do this? What? Excuse me. What is going on, man? Why does it give me a hard time? Is missing required argument flags? No? I don't think that even matters. Huh. How does that happen? Maybe it's because I dumped the operating system in... That could be why. I got something to do with it. Hold on. Also, in the Python interpreter, it looks like I can't clear the screen, which is kind of annoying, but that's okay. So f equals open. Let's do import OS. F equals open os.current current working directory plus tt. There we go. Okay, that's what we want. Yes, there's like a built-in open that we can use, and there's like an OS open, which is a little bit different. All right, so what we want to say is let's read line by line in TT till we get like 35 from the bottom. So we could say, actually, you don't even need to do that. You could do, I can do better than that. We don't need this in Python. We could just do tail 35 TT head 1. There we go. All right, this is probably the test case. I should have done that from the beginning. I don't know why I'm messing around with Python. I like Linux scripts and bash scripts and things. Okay. Did we get the right one? Oh, that's gonna take a while to check. I didn't think about that. Oops. Oh, that's okay. I'll take a moment. So yeah, I don't know what happened with this test case where everything else is correct except this one. Somehow something strange went wrong. I think it's our heuristic. We have something of a heuristic going on here with our check. It's kind of a greedy algorithm mixed with a DP algorithm. So as I said, the prioritization kind of changes in some cases. Okay, so it is the last one. All right, we got it. Nice. So we can get rid of everything else and just take this use case. And there we go. Okay, let's see. Also, we might get an invalid test case here because of the there's like an extra line at the end here. Oh no, oh they got it. Okay. All right, so we got one, and this is the test case. Now, why might that be the case? Why would we get one here? I gotta look at this carefully. So, a lot of negative numbers. Unfortunately, our DP doesn't tell us the path that we took to get down there. But somehow there's a way to get down there with 1 health. Now that doesn't make any sense to me. Maybe we should print the DP. Maybe we should print the DP array, or better yet, we could take this and just make this into a. We can actually see what this grid looks like. Oh man, that's big. All right. Oh, whoa. Oh, it's all in one line. Oh, now that's interesting. So this is a. Oh, whoa. This is if you have 1 row. Okay. So what happens if you have 1 row? Oh, I see. That is special. No kidding. Okay, so yeah, I think that goes back to the problem we had with like I don't know like how to correctly handle the first loop, I guess, something like that. Oh, that is a problem, huh? Okay. So works well for everything else except if you only have 1 row, you have run into issues. Yeah, one very subtle thing I did wrong. It's one tiny thing I did wrong. Teeny tiny thing. So what happens in our code? So we could, I think I know what's gonna happen with our DP, but we could print the DP just to get an idea. Oh, yeah. So. And we can also do. And we'll say. Yeah. Oh. I guess we only can show the last. Oh. Okay, so actually our DP is min f is the number of rows, number of columns. So it's just size 1. So previous is just size 1. initial rows, so it's set initially here, 0, 0. It's 407, and then process initial rows. So there's only, so it starts off at 0, and row is less than 1, which it is. So this shouldn't do anything though initially. And then there are no excess rows. Then you process the columns. And you start off at the rows. No row, right, 0. Column is 1. There's no diagonal here to look at, so D is 0. So D is less than or equal to 0, which it is. And so you select the second one, D plus 1 is less than min F, which it's not, so this should be false. D plus 1 less than min F is, we said min F is 1, so. Oh, yes, no, yes, yes. So there's no diagonal above to consider to the left or to the or above. And then, well, no. But if it's greater than 0, so I think it's, oh, I made a mistake. So the left side is equal to 0. This is confusing. Yeah. So the left side is D, and above is D plus 1. So if we can include D plus 1, that means D plus 1 is less than min F, but we can't include the left side because it's less than 0. I think that's the issue, right? Yeah. If D is 0, you can include D. Yeah. That's my mistake. So that's just a slight error here. And again, would have been better if we included. So the position is tricky though because we're actually modifying the position as we go. So start off at this position. We can process D that's at that position. Yeah, oh no, that's fine. This works. We're okay. Compile error. Oh yeah, we just kind of stopped in our tracks because I realized there's nothing's gonna print there. You have to be add a little more code to print. Wrong answer. Oh no. Was better, but not quite correct. How do you figure that? Oh, this is equal to. Yeah, that gets back to what we were saying about having 3 different functions that you have to modify, 3 different places. Yeah, it's because of the, I should have made that a lambda expression so I could have 1 spot for 3, but still wrong. So apparently that wasn't the right change anyway. Apparently that didn't matter. It's closer, at least, to the right answer, but it's still not correct. It's only off, it looks like the 407. It's only off by 407, right? Yeah, it is exactly that. Yeah, because the now why is that the case? That doesn't seem correct. Should take previous D every time, I think. Why do you think that would be? So what's interesting here is, oh, I see the problem. We added this twice now because we're processing this initial row. We processed this value, we added it twice. I think that's the issue. So really these should start off at 0, 0 then, I think, if we're gonna do this. Yeah. T is previous to D. And you're gonna add it to itself. Okay. In that case we can make these 0, 0s, I think. We're fine after that. Let's try that. I think we fixed our problem. Interesting, and I don't think we need to modify this anymore either. Oh, okay, nice. That works nicely. Yeah. Now, this isn't totally correct though, because this new val is going to be you take the minimum of B in the new val. This initial value is going to be quite large. This actually should be, I think, grid of A or 0, 0. This is a little bit confusing, I realize. Yeah, because I think it messes up the other calculations if we don't do that. Also, this does not need to be so large. It's a good thing we caught that very slight change or slight problem. How we do it? 2.5 hours we were on this. Excuse me. And my connection is kind of wavering a bit here. Oh, my connection is dying. What's going on? What happened? Oh, it's back. Okay. All right. Let's see. Wrong answer. No. 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 Oh, we got a lot of wrong answers now. Before we were mostly correct, now we're mostly wrong. What if we made this 0? Part of me thinks this should be 0, but I don't think it's going to work properly. So why is this wrong? What happened now? I mean, we had mostly correct answers before. Seems like everything's wrong now. So, okay, we'll go one by one. Let's take the head first. Okay. So this has a lot of things to look into. And for some reason, 1 is sufficient. I don't think that's true. So if we go back to what we had before, made a few different changes, so I'm wondering which of these changes caused problems. If I could identify that, that would be useful. Okay. How about this? No. So this was correct before, which is kind of peculiar. For these changes that we made. It's kind of a lot of code to change too. Go through all of the different, like what could be wrong. I think it has something to do with, yeah, it's basically coming back with, well, okay, we could process each step, I suppose. I think it actually should start off at 0, or no. I don't know what it's supposed to start off at, quite frankly. Okay. I don't know, man. All right. How are we doing on time? Yeah, 2.5 hours now. Wow. Okay, I think I have the right idea, but somehow I've implemented this incorrectly. It took a really long time to implement it incorrectly. It's painful. It's painful. But what could be wrong? But what could be wrong? Um, okay. So we're gonna get each of these diagonals here. Oh boy. What? Oh. Oh, I see. Okay. Just hit T1, T2. We'll do A and B. So we'll say excuse me. Yes. I think that works. Alrighty. 3 different spots again. That's what I'm saying, man. It's better. It's usually better to just write a lambda expression. Yeah, because until you have the code correct, you don't want to be like fixing errors in 3 spots over and over again. I might just convert this to a lambda. Oh, well, hello. Look at that. Whoa. Starts off initially all empty, 611, all 0, 0, negative 48. So what's interesting is that even with not starting off with 611, we still seem to end up with thinking we could use 1 extra. So all the way at the bottom, we get, oh, why I do want to see what the one at the bottom is. Excuse me. So actually, I can transport this program to my local, my local computer and run it. I kind of don't want to do that, but if we really want to inspect this, I guess we could do that in theory. Oh man, brother, this is rough. This is rough. What about like maybe the last? Yeah, we'll print the last one only. I don't know what could be wrong. Yeah, I'd have to go through. I'd have to go through all the things that could be going wrong here. All right. Okay. Now that's interesting. This number is enormous at the end. Oh, I see, but in the beginning. So we have a huge amount of positive health. But somehow. Now this wasn't wrong before. I'm fairly certain. Right, there was only like a couple things that were wrong before. Huh. I don't know what happened here. I do think maybe it's better that this is this one. Starts off at 0. So my question is, D is less than this position. Can consider what's at that position and what's greater than that position, or nothing else. Okay. And then here, now these are what they're supposed to be. That's confusing. It's actually when I changed these that I got the wrong answers. But these were supposed to be. Only reason why you wouldn't be able to use these values would be all right, we're gonna write a lambda expression now. It's getting way too challenging to kind of debug this in 3 different spots. Oops. So there's D. Call it in D. Min F we have a reference to, and previous we have a reference to. I don't think we have anything else to. I don't think we have anything else to check on here. I don't know. Can we do a const? It's a little bit different, but okay. Something like this. So we have a position now. It could be 0 or not. Oh, these could be, maybe that's why. These could be greater than equal to or equal to 0. Yeah, if they're both positive, then we want to use this. Maybe that's why. Okay, so, and then each of these cases we say T is equal to select of, we have position and D, right? Yeah. Okay, so what happens when we do this? Yeah, it simplifies things a lot. Nope, doesn't matter. I don't know. I don't know. Select here is 0 in D, and then here is also 0 in D. Something like this. Actually, this part of the code's the same too. I think this is just wrong for the initial diagonals. Yeah, it's actually, these are, for the initial diagonals, these are like this. I don't know. So if you're equal to the position, that's the confusing part. Yeah. So we should do if you're less than what's allowed. I think that's the problem. So what's interesting though is what's allowed is actually position +1 for the first portion. Yeah, so this is position +1 is the only thing that's allowed because, why is that? Well, now is that right? See, that's another question. That's kind of weird. Position starts off at min f -1, and you can only consider when you're looking at these diagonals, only allowed to consider oh yeah, that's interesting. Yeah, it's almost like our diagonal is sort of written off to the side and ending at that point. You can think of it that way. And the next diagonal then is sort of starts at the next position down. And you can't consider the position to the left. That's the issue. Which would be on the other diagonal would be the same spot. That's why. I think that's what's incorrect here. Potentially one of the things incorrect. Okay, that's a lot closer. And we also have should be 0 here, I think. And you notice actually the 611 is being added too many times. That's another issue. I think you should start off at really this should be row 1, I think. I think that's the problem actually. Yeah. Yeah, you shouldn't even process the first loop. The first loop's kind of like null and void. Oh, okay. What? Huh. Huh? Huh? What? Oh, no, it's correct. Okay. What? Wait, what? What is what is going on? What is happening? Hello? Excuse me? Excuse me? What is going on? Does that make any sense at all? don't know, man. Probably don't need that anymore. Get rid of most of these. Who knows, man? Who knows? Okay, let's try again. We don't need this. Let's go back to TT. Let's get all of our test cases again. So. Oh, didn't mean to do that. There we go. See how we do. So, what can we conclude from this here? I guess one, this is a kind of a complicated dynamic programming question. Two, it's tricky. It's tricky to code properly. There are some principles, right? So we mentioned, duplicated code. Also, we're not out of the woods yet on this one. Oh boy. Oh man. Okay. Excuse me. Which one of these is wrong? Oh man, yes, this is really tricky because of the sort of L shape that's created when you try to DP this over the diagonal. By the way, I think this would be like 15 minutes if I memorize it. If I just memorize this and use quadratic memory, like I'm pretty sure this is like 15 minutes. But it's not 15 minutes if you're trying to be optimal. It could take a while. Oh wow. Okay, there we go. 17, 18. Where is that? Our list here. Can we count that? Let's make a new. Can we figure out which index that is? Maybe we could save this as a file name, right? So let's do it this way. I have an idea. We're not gonna open it here, save it here. We're gonna go here. We're gonna close Notepad TT. Vim test, or remove test, by the way. Vim test. Paste here. I'm gonna find the use. Okay, we're going to awk the script and find out what that let's do it this way to begin. I equals 0. Actually, I think I is initially 0. We're going to say if I++, if 0 is equal to 17, 18, then print I. Excuse me. What? Oh, I did that wrong. Do we not? What happened? Okay. Almost lost my awk script here. Oh, all right. Okay. Did do that wrong. Five. Okay. we can head 5 of TT, tail 1. Apparently this is wrong. You're not out of the woods yet on this one. No, sir. No, sir. Okay. 749, expected 1718. All right. Okay. So 748, negative 748, 769. So why would this be wrong? I don't know. I don't know. Now my thoughts were that we don't need to process this initial row, and for some reason this causes problems if we do that. Runtime error. Now why would that happen? If we set our initial row here, oh, I see. That's probably why. That's probably because of the position. Okay, that doesn't help us very much though. Apparently that's not really the issue. Is this just a wrong algorithm altogether? Is that the problem? Is that the issue? I would be so sad if that's the case. I mean, at what point is it incorrect, or at what point are we wrong? So this the excess rows, I think, is probably the part of the problem. I mean, this could be added to the selection too. This portion. Could you just need R and C? And all this is the same as duplicated code too. I mean, maybe we'll just throw that in there also. I don't know. I think this heuristic might be wrong. That's probably it. Just check to decide which one or the other. I think maybe the whole algorithm start to finish is wrong. That could very well be the problem. Very well could be the problem. Yeah, I think this duplicated code should be added in there too. I mean, well, what was the thing I wanted to look at here? Yeah, these excess rows. Very tempted to run this locally, just so I can go deeper into what's happening. Wow, I was not expecting this to be so difficult, brother. This is like way harder than I was expecting. Maybe I should have verified it first with the memoized solution and then coded the DP, because the challenge of the DP solution usually is not so much the figuring it out, it's actually just coding it, like usually I convert from a MOI solution to a dynamic programming solution. And that's the hard part, is converting, not so much figuring out the answer in the first place. But maybe the answer for this is just wrong, and then I figured out, and this whole time I just been trying to code something that's just incorrect, which would be very unfortunate, we'll say. So that would be very unfortunate. Huh. Excuse me. Oh boy. Wow. Huh. Also, the amount that this is off by is really interesting. You see how this is negative 748. So it looks like we just need enough to start, and then apparently for the rest of this we can get through without a problem, which doesn't make a lot of sense. Maybe we'll just print the row. I think processing the rows is causing issues. All right, this is a case where we have way more rows than columns. Yeah, I wouldn't even know where to begin. Where as far as what's wrong. Okay, definitely. I think we should move this into the. Move this here. And not return anything. Let's make this void. Do have a couple things we add though here. We would add previous, or no, not previous, temp. And we would also probably put this on a new line and add RNC. And then select the RNC. Okay. How are we doing? Man, this is brutal. Oh man, it's like 3 hours to spend on this. Oh, I gotta go to sleep soon. Oh no, actually, I still have time. All right, so let's do that too. Oh. Alrighty, let's see how this goes. And grid we need also. So much context, but I think it's better. Yeah, I think it's better to not have that duplicated code all over the place. Okay. So yeah, this is the issue, right? You see this? Excuse me. Negative 71717. So that's how did we end up with 748 here? I think the issue is that no, that's not okay. That's revealing, but that helps. Actually, helps a bunch. So that's what we start off with. Then we take a look at the next values, and we say we can only get to, it's actually put this in a, so you can visually see what's happening here. We can do something like the following. Oh no, actually we word wrap. But we also can, we could do something kind of useful here. Could just delete everything there. Good. Okay, and we're gonna tr comma with a new line character. What? Oh, okay. Wait, what is happening? Oh, okay. Oh, okay. A few problems here. So we want to break this up into it's like every third comma we want to change into a new line character. I mean, you could do something like the following. Said whoa, whoa, whoa. I want to use S. Let me just say A with B. I just want to test to make sure I have the right syntax. There we go. So we use a regex here. We'll do or something like this. There we go. Okay. All right. Yes. So we want anything, comma anything, comma anything, comma anything. Right. We have 1, 2, 3. Actually, we can do it this way. Something like this. Does this work? I don't think so. I don't think it's gonna work. We could try it. This capture group with a comma placed with the same capture group with a new line character. Okay, I don't think it worked. I don't think so. Look. Interesting. New line character there. Huh. Yeah, that doesn't doesn't seem to be working. You could do You can do something like this. How many times is that? 1, 2, 3, 4. 4 times. You could say capture group 0 through 9. So this is any integer 4 times, which would give you, oh, actually negative numbers too. Okay. There's also a space 4 times. I don't know. It's the no. It's a negative number, so question mark and negative, right? That may or may not be there. And then I think it might be the other way around. I think you do this. So there's this 4 times, this capture group, right? I think I'm doing this wrong. With a comma and a space, 3 times. Maybe maybe I do just want to parse this. Maybe I should just write a quick Python script to parse this into a data structure and then print it line by line. I'm not really sure if it's easier to do it this way or to just parse it. Yeah. It's kind of tricky. Maybe I can write a recursive parsing routine. Let me see. Python parse. Oops. One more file to edit. Python written. Oh no. Okay. Still installs. I wasn't sure exactly what I did. Alright. I pressed some buttons of Vim and caused some issues. Okay, so you can take how do you get on from the standard in on Python? pipe in. Well, maybe we'll just open a file. I mean, the sys, right? Import sys. And so you could say sys.argv of 1. You could say f equals open. And you can say I'm going to recursively parse, and we'll have s. Yeah, we can do it this way. So what do we want to do? We want to say array. It's going to be parse f.read. That's what I want to do. There we go. And so we're going to say this is going to be recursive. So we'll say yeah, we'll just take substrings of all the pieces in between. It might be easier. Let's have a string and we'll just have indices 0 to say s equals f read 0 length of s. And we're going to parse AB. And we're going to say if s of a is equal to this, opening parentheses, then we're going to find, we'll do it this way, we'll say ret equals a list, and this will return ret. Say if s is nice and big so I can see it. Is the opening the first character, then we want to find, I think it's something like this, s.find, closing character, and we're going to ret.append, closing character. So it's going to be something like come back to that in a moment. Otherwise, what we're going to do is parse the next integer from the string. Yeah, actually, I think the way to do this is split on yeah, here's what we do. Here's what we do. We would return s.split. So we're going to have yeah, this is kind of interesting. Split on your comma values. And we're going to say int of x for x in split of x. Split of s.split. Yeah. So that will give you a list that you return. And if you're if you're opening, yeah, so you're going to recurse on here, I'll show you how to do this. So int, we'll call it y, or I don't know, end or something, or final. Now what's interesting is actually this should actually, no, it's the other way around. So it's going to be, if the first character is an opening bracket, then the last character should be an opening bracket. So you're actually going to substring s. You don't even really need AB, I think. How do I think about it? Because we know the format that we're going to get this in. So we're going to call parse on s, where s is going to be sliced. Step is 1. We're going to slice with 1 character and length of s minus 1. Or actually, it's yeah, s minus 1. Yeah. So we're going to slice s, parse that. If we see an opening bracket, that means that the final bracket is the last character, and so we're going to process the inside. And what we do is when we process the inside, we are going to split we actually should do this. Something like this. Turn parse of x, x and split of split on something like this. Yeah, that's a little bit confusing. Though what's going to happen is and also each of these x's should be when you clear the white space, I forget what that's called, when you trim. Same deal here. So you'll see the first opening braces. You'll call split on all the sub portions and trim, and then you're going to parse each of those, right? And whatever those results, you're going to gather all those up into an array. Excuse me. In our case, each of those is just going to be, you're going to call the same routine, but at one point it's just going to be a string, and you could split that string of integers, you could split that, trim, and return an array of the, yeah, I think this works. I think this does what we want. We're just going to print the array afterwards. So we can have our test program, right? Or our test, yeah. So we want to Python parse.py test. A is not defined. Oh. S of 0 really is what it would be. What? String index out of range. Oh. Let's see. Oh no. Did that twice in a row now. Well, I don't know. Strip. I did mean strip. What is print? What's happening? Huh. Oh, I see the problem. What is going on, man? Oh, I see. Okay. I totally... I'm doing it all wrong, man. I thought I was so clever, man. I thought I was so clever. So oh, that's the problem. Yeah, you can't just split on commas because of the oh, it's annoying. I see the issue. Oh no. No. Yeah. Oh, I see. Okay. Oh man. You oh, okay, that's part of why the parsing is challenging in the first place. Right. You would say it's not split, but it's like you kind of run a routine, so you kind of have like ret equals 0 or this, and you say kind of like a while loop or a for loop or something where you would iterate through each. Well, I mean, you could read. It's kind of like iterate through each closing parentheses, more or less. You can use a while loop. I mean, that works too. So while s dot find. So let's do a equals s dot find closing parentheses. We're going to say. Now this is really tricky too because this doesn't actually help you with this is really tricky too because this doesn't help you with oh no. Oh man. You can't if you have smaller excuse me. If you have smaller like let's say you have like a nesting level of 3 for your arrays, you have an issue because of the first time you see this closing parentheses, it's going to be one of the nested arrays, not the larger portion that you're looking for. Oh no. Uh-oh. Oh no. Yeah, you have to parse on the. Oh no. Oh no. How do we do this? Very challenging. It's kind of funny that this is what I was going to solve to help solve the other problem. But this is a hard problem too. Not that hard, but it's challenging. How would you do this? Basically, parse a nested array. Parsing a nested array. That's basically what we're doing here in Python, and then printing it afterwards. Well, if you see opening and closing braces, then you can process the inside and remove the braces, and that's going to go into an array wherever you process. That doesn't really work though. I guess, yeah, the reason it doesn't really work is because of well, you'd want to break this up into items, but you don't know how many items you have. Almost need to dig down to find out how deep you need to go until you can use a substring to get that first element. Oh no. Definitely want to use recursion here, but it's kind of hard to figure out how deep you gotta go. I want to say something like you can take a look at the next comma, and you can figure out how many brackets you have seen once you get to the next comma, and that tells you how nested you are. And then you can take the element there, and I guess nest, create a stack of I don't know if that's good though. Actually, no, I'm really not sure. You'd want to do this recursively, but it's hard to figure out how to do it recursively because how do you break up the array into the first section of elements? Can't just use symbols because you have opening and closing brackets. Well, what you could do is for the first element, so if the first element has no opening and closing brackets, then you can just take the substring up to the first comma But if you do have an opening and closing bracket, then basically you need to substring. You can use a stack to substring. That might be the way to do it. It's kind of expensive to do it this way, I guess. But you could maybe use a stack to figure out how deep the first element is that you're looking for, and then use the same stack to keep searching to the right for the closing brackets, so you can find all the opening brackets from left to right, and then all the closing brackets from left to right, and then that substring on the last closing bracket, that's your next element. So you can substring that way, and then you could parse recursively there. So what you can do is you can run that routine on every element of the string to get all of the substrings, and each of those substrings for each piece you can run your parse routine, right, recursively. And then so each of those you would not only can you run the parse routine, but you can append to your return vector. I think that's the way to do it. So yeah, you can take the opening and closing brackets and then substring each element in between. Right, so I think you would do it that way. Yeah, there's a routine with a stack where you can basically parse those substrings. The tricky thing about that though is once you have that first element and you substring and parse that recursively and add that to your return array, the problem you're going to run into is you have a comma, excuse me, and some white space. And you want to, I guess, skip your comma and skip the white space to the next character. And then similarly run your routine to see if there are any opening and closing brackets. If there are, then you need to, basically keep parsing until you've gone through your stack. So you blew through your stack through all of the opening and closing brackets. And if there are no brackets, then you can just go to the next comma and then run your parsing routine on that substring. So it's either between commas or it's you have to use the stack of brackets. But yeah, you want to go sort of between commas, or to the end of your string, right? Either in the next comma or the end of the string. And let's see here. Yeah, so if you parse something that doesn't have an opening and closing brackets, then what you ought to do there is actually parse that as an integer directly and add that to your return vector. So if you do this recursively in that way, I think it's sufficient. I think it's that simple. So we could try that. So this would be one way of parsing a nested array into an array in Python, or really any array. But yeah, so this is going to be interesting. So you do it's really a while loop, and I'm not sure exactly when it ends. And you return ret at the end of this. And the rest of this is kind of gone. We don't need this. So what I was thinking was, say if length of s is greater than 0, and s of 0 is equal to, now I'm not sure what this, I guess we could do a is equal to 0, and b is equal to length of s minus 1, and we just say while b is less than the length of s, something like this. We can, so if length of s is greater than 0, yeah, okay. And s of 0 is equal to an opening bracket. So we have a stack, we'll call it st. Really, it's a while loop. We'll have a sanity check. If length is 0, s less than or equal to 0, then we just return an empty array. So we don't have to mess around with this. So we could say while, so we're going to say x equals s dot find, and it's going to be from a. We're going to say while x is not equal to -1, we're going to say a equals st dot push or append. I think Python has stacks, but we're not going to use a Python stack. We're just going to use the Python list. So we're going to append to our stack one of these characters. You can really append whatever we want, but we're going to do it this way. A, and then updates to x, and x equals s dot find a, and then x1. So we say a equals x plus 1, while x is not equal to -1, and x is less than length of s. So take the b is less than the length of s, x equals s dot find a from 0. So if we find this opening, yeah, so we're gonna add, as I said before, we're gonna find all of these opening brackets and count all of them, right? And then we're going to say we're going to have just beta, we'll call it. So alpha, we'll start off at we'll start off alpha at some value initially. Should we use A? I mean, I guess A is fine. So then we'll say beta is equal to yeah, I mean, we could do this. So then x equals, so we'll say while st, we're going to say x equals s dot find of a. So, assuming this never happens, this really shouldn't ever happen, but we find a bunch of opening cases. Oh no, this should happen actually at some point. This should go to -1 at some point. Once you hit -1, right, we say find the closing brackets, and we're going to st say if x not equal to -1. We should say st pop back, or just pop, and then I actually don't know. I think you just call pop on it. Yeah, it's just pop. Okay. Okay, so while we have something in the stack, we're going to update x to find a x is not equal to -1. Then we're going to set x to x plus 1, really, or a equal to x plus 1, right? So one character after the closing bracket. So x equals find a, so we find that, pop from the stack, and set x to the next character, and then a to the next character, and then update x again. So now at the end of this, a should be pointing to, so what's interesting is x equals find a, we're going to say alpha equals x, and then at the end of this, it should be beta is equal to x, and we're going to say ret.append parse of s alpha beta. Okay, so oh wait, what's going on here? Hello, Industrial Insanity, welcome, hope your day's going well. Hello, I'm this is what we're doing. Okay, I was tinkering with this problem on LeetCode, which is a hard problem, and I wanted to find out, I wanted to mess around with this test case that I made, but the problem is the test case is it's kind of ugly when you look at it in a Word document, and so I thought, oh, let me just write a quick script to take this matrix and print it in a way that looks good. So we're going to have an array, so each array will get its own row. And then I realized, oh, like this isn't as easy as I'd like it to be. So I thought, okay, I'll write a script that parses this array, and then it parses in Python and then prints what I want in Python. And then I realized, oh, that's not that simple. If you wanted to parse a nested array, it's not the most obvious thing if you're parsing it from a string, right? So that's what we're doing, parsing a nested array, which is actually not that simple. I think it'll be okay, but it's not that simple. So we have, so what we're going to do, the algorithm we're going to do is we're going to take each element and we're going to create substrings for each element and parse those substrings recursively. But in order to get each element, since it could be a nested array, we've got to build a stack of all of the opening parentheses or opening brackets and all the closing brackets in order to figure out how much of our string do we need to substring in order to parse. The next thing is also we need to separate by commas and white space. So yeah, this is going to be interesting here. It's going to be interesting. And we're going to trim this also, in case there's any white space that might be in there. Yeah, so now we pop our stack, we get A, so beta is going to be A, and alpha is going to start off at A as well. Or alpha should start off actually at X. And X plus 1 is one character after, right? So, okay. Yeah. So then, what happens is we parse that element, and what we would do is then say there's any amount of white space. So I'll say X, then s.find from A to a comma. So if X equals -1, or if X equals -1, then I'm not sure what B is supposed to be actually. Then we can exit the loop. So actually, no, we don't exit the loop. We would say ret.append parse of, and I guess we could do, so if there's no more commas at the end, there are a few issues here too. So we do something like this. We'd say if s of 0 is equal to an opening, and first things first, we're going to trim s. Just trimming all over the place. If this is an opening, if this is an opening bracket, then we would do what we were doing here. I don't know if that's what I should do. I don't know what I'm supposed to do exactly. I don't know. And otherwise, oh, we could do pass here. Otherwise, you're going to return, I think you just return int of s. Yeah, so if you're not opening and closing, okay. X starts off at 1, right? This is kind of interesting. So, oh, I'm not too good at math, but I can do some things. Yeah, fair enough. I'm not very good. I'm okay at math, but I wouldn't say I'm good at math. I wouldn't say I'm good. I'm also, I messed this up. I messed it up. I think what I want to do is, what was I saying? Wait, the idea was, you see an opening bracket, there should be a closing bracket at the end. Yes, we assume, yes, so if there's an opening bracket, then we're going to set S equal to S sliced away, slice the opening bracket away, and slice the last character away too. Remove the opening and closing brackets. And we'll set X equal to 0. Now, that's, yeah, so we can remove the opening and closing brackets and then process the inside, and then we're going to have a return array that we return. Otherwise, we're going to return an integer. Yeah, that's all we need. Okay. So this is kind of complicated, but basically, if we see an array, then we assume the inner substring of that array. We've got to recursively parse each of its pieces, and we're gonna first parse out its pieces, and then each of those pieces we're going to recursively parse those substrings. If it's not an array, we assume it's an integer, and we parse the integer and return it. That's the idea. So now we say, okay, so now if the now we've removed the opening and closing brackets. Now we've got to count for the first element. We've got to count how many brackets there are, the opening and closing brackets, if there are any. That's what we do here. So we say x equals a, opening bracket. If we go to -1 and st is empty, and the stack we could put over here. So if we go immediately -1 and the stack is empty, alpha should actually start off at it would be wherever x is, I think. Yeah. So alpha starts off at x. And we say we find this opening bracket. So we're gonna work through all these opening and closing brackets, and beta is going to be where a is. Excuse me. And we trim this string, parse it, append, and the tricky part here is that's recursive. The tricky part here is now we want to go to the next element, right? So we see this comma, so we set x to this comma, and if it's -1, so we went to the end, then, excuse me, so if there's no comma, then there's no other element to process, I believe. Let me think about that for a moment. Yes, I think that's the case. Yeah. So if then we can break. Otherwise, we would set x equals x plus 1. So if we find the comma, if we don't find a comma, we're done. We got all the elements. If we do find a comma, then we update to 1 past the comma, and then we repeat. Our while loop keeps going. We have this alpha beta, and we append. Once we break at the end of this while loop, then we can return ret. At the end of all of that. Okay. This is kind of complicated. Can you do two-step equations? You mean differential equations? Is that what that is? I haven't studied differential equations in so many years. I attended university, how long ago was that? 20, so I graduated high school like 2010. So that was 11 years ago? Yeah. And I attended university pretty much shortly thereafter. And I studied maths like the first 2 years. So that was like 9 years ago. So I studied differential equations like 9 years ago. Yes. Yeah. I'm sure it's been 9 years, but I'm sure I could, if I'd have to go look it up again to remember how to do it, but I probably could. Probably could. Two-step equations. I don't remember what those are offhand though. What's a two-step equation? I don't know what that is offhand. I know multivariate calculus. I know like partial derivatives. I know differential equations. Not like to a great degree, you know. And obviously, like, it's almost a decade ago that I studied this stuff, so like I don't remember a lot of it either. But I remember being, oh man, that's like takes me way back. I haven't looked at like maths, like just pure maths, like calculus, in like almost a decade now. That's wild, man. That's wild. I appreciate you asking me about that though. I'm in high school. Math is one of the classes I actually enjoy. Oh, really? Whoa. Two-step equations. I don't know what that is. So hold on. Well, we can find out. Yeah, math is great, man. Math is a lot of fun. They're teaching calculus. There's teaching calculus in high school. That's kind of difficult. I remember when I was in high school, that was like that was like at the very end of the curriculum. We would do calculus. Let's see. Step functions. Let's go to Lamar University. Lamar. Oh, there's a pro feature for Wolfram Alpha. Oh yeah, you probably know about Wolfram Alpha. You could use Wolfram Alpha to do maths. So if you wanted like, I don't know, Fibonacci. There you go. You can get some information about the Fibonacci sequence. Oh, that's interesting. Actually, that's not the formula I use. There's a better formula than that one. But yeah, you could do like integrate, you know, x squared. Well, you probably already know that one offhand, but you could do that. So you can, you want to help with your maths homework, you could use Wolfram alpha. You probably already know that. But what is a two-step equation in differential equations? First order differential equations, linear equations, separable equations, exact equations, Bernoulli differential equations, substitutions, intervals of validity, modeling of first order differential equations, equilibrium solutions, and Euler's method. Second order differential equations. I don't even remember. Oh yeah, now I see that. Yeah, I remember this now. Okay, that's what a differential equation is. First order, second order. Eigenvalues and eigenvectors. Whoa. Oh yeah, systems of differential equations. Now look at that. Whoa. Okay, I don't know if you meant differential equations or just regular like two-step maths equations. I don't know what a two-step equation is. We use $300 conciliators to help us with it. What's a conciliator? What is that? They're not calculators. What is that? Or did you mean? What's a conciliator? Or are these calculators? Do you mean? I don't know. I'm so confused. I'm really confused. Yeah, because there could be calculators that are expensive that you would use for maths. A conciliator, I wouldn't call a calculator a conciliator. And then I don't know what a two-step equation is. I mean, you have like really basic equations that have like a couple steps to solve, and then you might have a step function in your differential equation. Or it's not really differential. Like you have, okay, so hold on. There's, well, I'll just say I don't know. I don't have enough information to really know. There's like a lot of stuff. There's also recursive equations, like Diophantine recursive equations. I forget what they're called. They have a difference equation. That's what's called. That's what I'm thinking of. Second order difference equations. Yeah. Difference equations are pretty interesting. These are fancy. And these are useful for computer science, I think. Yeah, difference equations is really interesting. Anyway, okay, let me get back to what I was doing. I don't know, man. I don't know. Calculator, level $300 calculator is bad spelling English. Oh, okay, got it. Can you show me an example of what you're describing? Because I'm trying to figure it out, but I don't know what a two-step equation is. I don't know what that is. Also, I think we're done with this program. Oh. Oh, there we go. Oh. Why do I keep saying trim? Strip. It's quite the name for a function. I like trim better. Slice indices must be integers. What? Huh. I don't know. What's the issue? I wasn't expecting that. 9a minus 2 equals negative 65. Oh, okay, I see. Yeah, I do know what those are. Yeah, that's a linear equation. They call it a two-step equation. Typically what you do is you'd have, another way of writing this is like this. You can use variables. So you have ax plus b equals c. And so your general solution is c minus b over a, right? Subtract b from both sides. And then divide by a on both sides. And there you go. There's your two-step function. So in your case, 9x minus 2 equals negative 65. A is 9. B is negative 2. And C is negative 65. And so you can say x is negative 65 minus negative 2 over 9. This gives you a negative. It looks like you can add negative 63 over 9, which is 7. Yeah. Did I get that right? Yes. Very good. You can do it that way if you want. That A equals 7. Yes, sir. I agree. I agree. Now my question is type error, it says. My question is, where's the type error occur? Test. Done. I just want to verify that that's the right spot that this is occurring at. Yeah, test 10 and test 20. So how come does this not work? Is that what? Slice indices must be integers. Huh. Where is that coming from? Find. Maybe I need to. That's weird. I don't know how that's. I don't know what the issue is. Maybe I'm using the wrong routine. That's very possible. Problems like the one I typed out, I can easily do, but some are harder than others. Can you give me a hard one? Can you give me one that you're struggling with, or that you've seen that you find hard? What am I looking for here? Python docs find. Yeah. Looking for the built-ins. I think it's a library reference. Built-ins. Okay. F. Find. A, B, C, D, E, F. No. Okay. Language reference. Somewhere in here is strings. Nope, not language reference. Library reference. Strings. Built-in types. Okay, we're looking for strings. String methods. There we go. Okay. So somewhere in here is a find. There it is. Oh. Huh. Oh, I did it backwards. That's why. Okay. Got it. I see the problem. I see the problem. I thought it was the other way around, but okay. Stand corrected. Yeah, I was under the impression that the find routines were the other way around. We can remove these now. It would take a bit to type out, but I can handle these problems. Huh. Yeah, type it out. Feel free. Feel free. But some, you said some are more difficult. I'm very curious. Well, if it's too much, you don't have to type it out. But I would like you to, so that way I could see it. You know, so I could see it. But that's okay. You don't have to if you don't want to. Certainly not. Oh. Typo on my part here. Oh. I think I got stuck in an infinite loop. Uh-oh. I wasn't expecting that either. Oh. It's a different loop that I get stuck in. It was one of these loops, huh? Whoa! Whoa! What happened? Huh. Oh, I see. I think it might just be taking a while. Could just be really inefficient. Yeah, I didn't really think about that. This is kind of a large test case. It might just be taking a while. Let's see. Let's go. Oh, we don't need that. I was working on that. It's an interesting what that is. I may or may not have hacked a server not too recently, or not too long ago. I'm gonna keep that around though. All right, we're gonna have something like this: 1, 2, 3. Okay. We'll have 100, 5, 2, 20, and 6. There we go. Okay. I think we're getting stuck in an infinite loop. Yeah, I think so. So we're going to work on test 3, but why would this occur? Whoops. I don't know how I did that, but okay. So we have 1, 2, 3. 3 opening and close. No, that shouldn't be the case. Oh, I see. Oh, I see. Right, I see the problem. Ah, this is a very subtle thing. Okay. Oh. Oh, I see. Okay. Okay. This is an interesting question. So the problem is that we need to figure out how many opening parentheses we have, opening brackets we have, but we don't even want to go all the way off past the first comma that we see. So we want to stop at either the first closing bracket or the first opening or the first comma to count how deeply nested we are. Can't type it out because the phone is not the best equation typer. Oh, I see. Ah, I see. You into historical stuff? Yeah, absolutely. Yes, sir. Yes, sir. Oh, man, that's a tricky algorithm, man. This is a hard one. Excuse me. So, what we want to do is actually we stop when we find a closing bracket, really. Yeah, okay, so we can do this. Huh. Oh, this is very, very tricky now. Okay. I don't want to do this. So if there is an opening bracket, so if there is none, then we let beta equal A. Yeah, so, Now, this is a very tricky thing. Wow. Oh, man. I'm struggling with this algorithm. I collect a lot of history things. Oh, sure. That's not a bad idea. That's not a bad idea at all. Oh, I have hit such a problem. Whoa, what a problem. What I want to do is that if it's an opening, if there is an opening bracket, then I want to close off the string with a closing bracket. And then we'll count all of the first closing bracket, which is guaranteed to be 1, if I leave the closing bracket at the end. So I think what we would do is, I think we're on the right track. We can just say, if so we have this while loop, we're going to say, right, X is this first opening bracket. So if X is equal to -1, and then we can say, Y equals find comma of A, and say ret.append parse S of that would be A to Y strip, and then you would update A to move A along to, is it A or X? I don't know. Oh, this is so tricky. Find the next comma. Say T is equal to, so if Y is -1, then so we'll say T equals S of A, otherwise T equals S of A to Y, and we would update A to Y plus 1, and we're going to append t, strip t. Right? I do something like this. That's if we don't find an opening bracket. Now if we do find an opening bracket, otherwise, we could do some of this code here, where we set all of these values. This is a complicated piece of code. Complicated piece of code. I've been doing this for 4 hours. Yeah, I've been going, yes sir, actually almost 5 hours now I've been working on this problem. Yeah. I go until I'm done. Go as long as I can. So now we say, we find the opening bracket. If we don't have an opening bracket, then we'll break off on a comma. If we don't find a comma, that means we finished, more or less. Yeah, actually in this case you would break, or you wouldn't break, but here you would update a to, we'll use a instead of x. I think it's better. Here we could say is length of s. And you would parse our sub portion. Now, right, we'd set up t appropriately. Move a past this y value, and then keep going. But if you do find an opening bracket, then we want to count the number of opening brackets. Excuse me. We could just say c is 1. So you expect to find a closing bracket somewhere. So y is going to be, now, y could be a comma, or, so we're going to count the number of brackets either to the next comma or to the next closing bracket. Yeah. And there's guaranteed to be another closing bracket, right? So now we say, and x is less than y. And we update x equal to s.find the next opening bracket. So while x is not equal to -1, so find another opening bracket, we append it, update x, and increment a to past x. So we count, and we don't have to actually append to st, we could just increment c. I'm thinking, yeah. And then finally, while c is greater than 0, we're going to look for the closing brackets. And if we're not at the end of the line, towards the end, then we could decrement c. And that should put us in the spot we want to be to take our final, what do they call that? Our nested substring, right? Now we could recursively parse that, strip that, parse it, and append that. And now the tricky thing is, if we are, so we take x, we find the next comma, and if we're all the way at the end, then now there's no more elements if we're at the end, so we could set this to length of s. Otherwise, we just move x past the comma, or move a past the comma. So something like this. Let's see. It looks like we hit infinite loop. Dang. Thanks. Yeah, thank you. I try. Alright, now we're getting stuck somewhere. Now why might that be the case? Where are we getting stuck? Let's start with that. Oh. Oh yeah, you can send minus equals 1. That works. Oh, this is supposed to be A. That might be the problem. This should be immediate too. Alright, where are we getting stuck? Okay. It's probably somewhere in here in these two while loops. What else do you enjoy? This is pretty much all I do. That's pretty much it. I used to play football when I was younger. I used to play sports. I used to exercise more. I used to do a lot of things, but for the most part, this is like all I do because I'm unemployed right now, so I'm working very hard to firstly find a job and secondly get through all of these LeetCode problems so that way I can be fully prepared for programming related jobs and programming related tasks and things like that. I gotta really have to do a lot of practice, and obviously I struggle quite a bit with certain things. Like as you could tell, this particular problem I'm struggling quite a bit, both on the LeetCode problem itself and also tinkering with test cases and whatnot. So that's pretty much it for now. But in the future, I'll probably work on other programming things. I like to play Minesweeper every now and then. But yeah, I'm like, I don't know. My time right now is very, just say things are challenging. I'm a Christian. There's that. I love the Bible. Love God. Not sure if anyone's explained that to you, what Christianity is and why it's important. That's actually that's the most important part of my life is being a Christian, loving God, finding my identity in Christ. Yeah, serving God, doing what God wills me to do. Program drones or games, or better yet, make a game. I'm a Christian too. Oh, you are? Hey, praise God. I didn't know that. Oh, wow. I'm so glad. Oh, I'm glad to hear that. Glad to hear that. All right, pop quiz. What do you tell someone if you meet somebody and they have 5 minutes left to live? What do you say to them? What do you tell them? Invalid syntax, line 27. Oh. Wait, what? Oh. What is invalid? What do you mean it's invalid? What do you mean it's invalid? What do you mean it's invalid? How is that? Thank the Lord for what he gave you. Don't feel sorrow, for now you are free with our Father. Almost. Almost. Suppose that person is not a Christian. What would you tell them? Actually, that's actually the point of the question. You would want to, I guess, first verify that they're a Christian, and then second, if they're not a Christian, what would you tell them? So this is invalid syntax, apparently. I don't know how that came to be. My Python interpreter doesn't like this line of code here. Oh, it is invalid. I'm sorry. I don't know why it is invalid. Alright, 1030, 1010. Okay. Let's do, so we're getting stuck in infinite loop somewhere here, but I don't know why. 25. Alright. Oops. Okay. So 40 is the one. Oh, I see. So I guess I don't know. Local variable x reference before assignment. That's not true. That's a hard question. If you could do one last thing, it's not too late to ask for forgiveness and have faith. I don't know. That's a hard question. Okay. So, in the Christian faith, as far as I understand it, you have the good news and the bad news. Really, the bad news and the good news, right? God has his justice and God has his mercy. You can't have mercy without justice, right? So the way it works is justice is you've done something to infringe on the authority of God, right? You've sinned against God, done something you don't have the authority to do, and so you need to be punished for that, right? It's like breaking the law. And so that's justice, is that you would be punished for that, right? If somebody broke the law and did something to you that they didn't have the authority to do, then they would have sinned against you, and it would be justice for them to be punished, right? That's the justice of God. The mercy is when you deserve to be punished for something you've done, something evil you've done, something wicked, sinning against God. Deserve to be punished, deserve it. However, you have forbearance, that you either won't be punished or you won't be punished for a while, right? Forbearance means to sort of not do something for some time. So not do something that you would otherwise were going to do. So that's mercy, right? That's God's mercy. So his justice is that, specifically, that we have to be punished for our sins. And his mercy is that he's not going to punish us through Christ. Which is a bit complicated, and we'll get into that in a moment. But it's not too complicated, but we'll talk about it. So that the bad news and the good news. The bad news is that we've all sinned and fallen short of the glory of God. We've all lied. We've all stolen. For those of us who are of age, we've looked at a woman with lust, for the men, and usually women as well. Jesus said, if you look at a woman with lust, you've committed adultery with her in your heart already. We've all hated, right, which is murder of the heart, and we've all blasphemed God, which is a sin, right? The Ten Commandments. It's very serious, actually. In the Old Testament, you'd be murdered, you'd be killed for blaspheming God. It was that serious. That was part of the Old Testament law. Yeah, those are just a few. We've all done those things, so we deserve the wrath of God, the bad news. And we deserve to go to hell, right? God is perfectly holy and perfectly just. He cannot let any sin go, let anything we've done that's evil go without justice, without punishment. So he's perfectly holy and perfectly just. However, he's also extremely merciful. So what God did, so that you and I don't have to go to hell for the sins that we've committed, the wrath of God that's waxed, that's hanging over our heads, the wrath of God that we deserve. God sent his only begotten Son, Jesus Christ, born of a virgin, to the earth, fully God, fully man. He lived for 30 years, perfectly sinless, perfectly righteous man. The only man to have ever lived a perfect life. None of us have, not even for a day. Any of us could, and or I couldn't. And what he did is that he sacrificed himself on the cross and imputed his righteousness to us, and he substituted himself for us on the cross, so that all of the wrath of God was taken upon him in the 3-hour period, roughly 3-hour period, on that day. All of the wrath of God was poured out on him. The wrath that we deserved was poured out on him. So, and he let himself die, was placed in a tomb, resurrected 3 days later, and showed the world that he had authority over death. And he showed his disciples, and he was indeed God. He had authority over death. And he told everyone to repent and believe, and to be regenerated, to be born again, to be made new in Christ. And so, through Christ's blood, through his sacrifice, we can be reconciled with God. So when God sees us, when he judges us, he sees Christ instead of us. He sees Christ's perfect life instead of our wretched, sinful, and evil lives. And so that's the gospel in short. And if you met a person that was dying, had 5 minutes left to live, you would try to explain that's the good news. So the good news is Christ. The bad news is that we've all sinned and fallen short of the glory of God and all deserve to go to hell for it. And the good news is that Christ came and confronted sin, and now we're called to become more and more Christ-like, and after having been regenerated, to confront sin in the world, to follow Christ, to make disciples, and to repent of our sins, turn away from our sins and turn toward Christ instead. And what is the other part? Repent of our sins, believe that Christ is God, that he does indeed have authority over death, and to be made new creature in Christ. So that's the good news, right? Is that we have that, we can do that, we have that. So that's the bad news and the good news. And what you would tell a person who has 5 minutes left to live is first ask them if they're a Christian, ask them if they can explain to you the gospel in a couple of minutes or two, if they know the gospel. If they can, actually, literally what I just asked you is what you would ask them. Can you tell me, the gospel? And if they don't know it, then tell them that. I think if they only have 5 minutes left to live, you have to tell them, the bad news and the good news. And basically pray in the last 10 seconds that they would be regenerated. That's what you would tell them before they die. That's the gospel in a few minutes. It would be, you wouldn't have enough time to really verify what they know if they are Christians. I think you just have to tell them the gospel. But this is how I check if another person says they're a Christian. This is how I check that they are indeed a Christian, is if they can tell me the gospel in a minute or two. And so because a person is dying, if they're one of God's lost sheep, then you'd want to tell them the gospel so that they don't go to hell. That would be the reason why you do that, by the way. That's what I'm missing. I'm still learning new stuff from my grandparents. Sure. So if you're curious about Christ and God and what's expected from you, what I would recommend is I'd recommend reading the Bible, and I'd recommend reading John, the Gospel of John. In the beginning was the Word, and the Word was with God, and the Word was God. The same was in the beginning with God. All things were made by him, and without him was not anything made that was made. In him was life, and the life was the light of men. And the light shineth in darkness, and the darkness comprehended it not. There was a man sent from God, whose name was John. The same came for witness, to bear witness of the light, that all men through him might believe. He was not that light, but was sent to bear witness of that light. That was the true light, which lighteth every man that cometh into the world. He was in the world, and the world was made by him, and the world knew him not. He came unto his own, and his own received him not. But as many as received him, to them gave he power to become the sons of God, even to them that believe on his name, which were born not of blood, nor of the will of the flesh, nor of the will of man, but of God. And the Word was made flesh and dwelt among us, and we beheld his glory, the glory as of the only begotten of the Father, full of grace and truth. John bare witness of him and cried, saying, This was he of whom I spake. He that cometh after me is preferred before me, but he was before me. And of his fullness have all we received, and grace for grace. For the law was given by Moses, but grace and truth came by Jesus Christ. And it continues. I'd recommend starting with John, Gospel of John. And you definitely want to find a pastor, too, a church, and listen to your pastor. And read the Bible. Just read the Bible voraciously. Ask me any questions if you have any questions too. And the Bible's pretty long. I still haven't read the whole Bible. I'm still working on that. I've been kind of distracted, as I mentioned. I'm unemployed at the moment, so I need to find a job. But I do spend quite a bit of time listening to preachers, what they have to say, and reading scripture. The Bible is amazing. Nothing short of amazing. But you'll learn quite a bit about the faith from reading the Bible, what it says in there. And there's a lot of commentary online you can read and learn about what other people have explained and other people know about it. Screenshot it. John. Well, I don't want to take a screenshot, but it's just Gospel of John. I have the Bible in my fridge, and I have it next to my artillery shell. Yeah, okay, that's good. Yeah, read it. You'll learn that way. That's the best way to learn, is to read the Bible. Pastors can help. Other people can help. Ask questions. Go online on the internet, and if you have questions, learn on the internet. There's actually a few people who are really good to listen to. This guy I like a lot. Highly recommend this fellow. Living Waters Ministry, these guys. Highly, highly, highly recommend. Check out this guy's channel. It's actually why I became a Christian. Sort of, it was his his evangelism that called me to repentance. I did screenshot. I mean, oh, you did. Okay, very good. Yeah. The Gospel of John. Gospel of John. Recommend it. Highly recommend it. Okay, so somehow we have a local variable x reference before something. Oh, that's actually, let's see what the problem is. S. Okay. Alpha reference before assignment. Okay. I think this is. No, there we go. Almost. Missing some things here. Didn't work. Almost got it, but didn't work. Do you know Melito? I do, absolutely. Melito comes by from time to time and says hello. And I appreciate it. I'm grateful. Grateful for his company. Alright, so this is not quite correct. Oh yeah, well, we should debug this though. So, test 40. So 1c x is negative 1. So c is 1, a is 8, and x is negative 1. I see. So what's interesting here is where is this x alpha? Should really start off at a, I think, not x. No, should start off at x, actually. I was wrong. So c is 1. We find this variable. We don't need to do this again. Oh, no, I see. That's why we do it again, though. Well, no, it's fine. So y is find the next value. Closing parentheses. Or a comma. First of these two. And x is not equal to negative 1. X is less than y. Going to increment c. So I think this actually should be 0 initially. I think this actually should be 0. Oh, it worked, or almost worked. We're a lot closer now, but we're missing the last numbers, 5 and 6. Very close. So Hmm. Oh, that's what I did wrong. Ah, yes. No. Huh. Not quite. He's pretty cool. Yeah. He's your friend? One of the videos on Living Waters is Ozzy Osbourne credits Satan for COVID protection. What the heck? What? I have in my class, some kids in my class think Satan will give you what you want for sacrifice. Like what? I never liked him anyway. Wait, I'm really confused. Who did you not like? And then also let me know if my voice is too low. I'm keeping my voice down because it's getting late over here. I'm gonna start whispering. Turn up the volume a bit. Start whispering. Who did you never like? What are you referring to with sacrifices? And Satan for COVID. Yeah, well, Ozzy Osbourne is not. Oh, you never liked Ozzy Osbourne, probably. Yeah, Ozzy Osbourne's not a Christian. Ozzy, I never liked. Gotcha. What the? Yeah. So, oh, I should mention something. So I don't curse, and I don't say what the heck or what other things like that. Even like minced cursing, expressions of anger and frustration like that. I avoid those things, and I can kind of explain why, but it has to do with being a Christian. I can go into detail about that actually. Maybe not right now, but I can do that. It's true. So it looks like we do need to add just right here. Oh. Oh. Oh, we did it. I almost did it. Um, excuse me. So we got 105, 2 with an extra one, 20 and 6, and then an extra one at the end here too. Let's see. Um, oh, it worked. Hey. Huzzah! We did it! Did we? Yes! Yes, we did! We did it! Hey! Kids in my class thought that Satan was all that, but I had to tell them all it's not what you think, and I had them think what they had said, and they thought that wasn't rational as well. Rational or good. Huh? What do you mean? Like, you told kids in your class that Satan wasn't good? Is that what you're saying? Alright, now we're going to do this on... There we go. Alrighty. Now that we have a parsing routine, which I thought this wasn't going to take so much time for this parsing routine. This could be useful, but you know what I want to do. I want this to be a module that I can import. I don't do that too often, actually. Import Fibbo. So actually, it looks like it's as simple as we should have had at least one line here. So let's have a have a new them. We're going to pretty print. Now this we're going to import sys from parse, import parse. And now we're going to say file. It's going to be our file name. It's going to be sys.arg of 1, argv of 1. Say f equals open, file name, read. We're going to parse, say array equals parse f.read. And now we're going to say for I in range of array, length of array, we're going to print array of I. There. How about that? So now let's pretty print test 2. Okay. They thought Satan was good. Oh no. That's terrible. I would recommend this. It's all well and good to see why Satan is not good. However, I'd recommend if you could try to convince them that Jesus is good, I would say try to give them the gospel if you can. The bad news and the good news. I would start reading your Bible a little bit first, and I would start with getting yourself sorted out with God first. Read your Bible, talk to your pastor, watch some sermons online, watch some evangelists online, find a good Bible-believing church, spend time with the Bible, and then once you grow yourself, and I'd recommend you can try sharing with your friends, but once you grow yourself, then you can try to evangelize to your friends and try to explain to them why we are not righteous and where we are not good, and why Christ is, and why we need Christ in order to be reconciled with God. And you start with that. And if they believe in Christ, then they naturally will hate Satan as well. They'll love what God loves and hate what God hates. Oh, not test 2, but test 3, I think, is what we want. There we go. Ah, that was the goal all along, by the way. What I was trying to do was pretty print this array. I think I did this wrong, though. I think they did this wrong. Because I think the answer had 4, not 3. Oops. Uh-oh. Uh-oh. Huh. Uh-oh. This was wrong. This one's wrong. No. I lost a number here. 748. We lost 769 somehow in there. I don't know how we lost one. Uh-oh. Uh-oh. So our parse routine is not correct. Oh no. Oh no. I did, but the problem is that most kids these days don't really care. It's sad. At my school, they date the same gender and sow weed and just a bunch of crazy things. But yes, I learned with the gospel. I learned new things with my grandparents a lot. I will learn the gospel. Praise God. Yeah, praise God. Try to get, if you can try to get either homeschooling from your family members, or if you can get into a like a private school or a school that's not like public school. Unfortunately, public schools are really, really rough on Christians, especially for their faith. Public school is not good for anybody, really. Public school is a mess. I'm sorry you find yourself there. Yeah, I don't know. I'd even encourage you to, like, if you could drop out of school and get your GED and then like start your life sooner instead of wasting time in public school. I mean, talk to your parents about it, talk to your grandparents about it. Don't just take my word for it. But I'd recommend that. I'd say public school is basically like a nightmare spiritually. It's just really bad all around. It's really unhealthy. And like, yeah, you have like, basically you have like, yeah, it's bad. Let's just say it's bad. Just say it's bad. I'll keep you in my prayers. Keep you in my prayers. I'm sorry to hear that kids are doing drugs and dating each other and when they're kids and having homosexual relationships and things of that nature. I'm sorry to hear that. It's really, really difficult. It's really difficult. Yeah, I don't know what to say other than that's really hard, and I'm sorry to hear it. Sorry. That is difficult. So I do have an issue here, which is, so somehow we terminate too early. I think we skip a number somehow. Find x, we find y, which should be a comma. We say alpha equals x, y is that comma, or it could be the end as well. If y is -1, set y to this. Oh, I see. Okay. X is not equal to -1. Right, it's not. And it's less than y. Find the next, keep finding these. Increment a past this opening bracket. So start with an opening bracket. And that is one bracket that you find. It should be a 1. And then, oh, I see. Will you add 1 first for here? First bracket that you find. You add 1, then increment beyond that, and then find another. And every time you're in here, you add 1, and then once you're done, oh, I see. Okay, that's correct. Yeah, that's right. And then you decrement 1 when you find the closing brackets. Yeah. Okay. And if x is a closing bracket, you decrement by 1. And once it's no longer, then you should end up at 0. And somehow end up skipping something in here though. Okay, I'll read in a moment what you've written. Excuse me, but there's something here. When we take the internal array, so we parse, strip and parse, and this part will have opening and closing brackets. So now let's say we work on this. We remove the opening and closing brackets. And when we have no more brackets, we find y, or find the comma, and parse t, and we update a to y plus 1, and continuously parse. Now what's confusing here is printing t. Okay. Give me one moment. Whoa. Okay. 748-818-626-337. Hold on a second here. What about 769? 748, we missed 769. What happened? What happened to 769? Oh, well, that's not good. Well, that's not good. Maybe it's the find routine. Maybe I'm running it, using it incorrectly. Oops. Tag stack empty. Okay. Lowest index for the substring is found within the slice start and end. Oh. Optional arguments start and end are interpreted as in slice notation. I could use in. Well, this is a problem because no, this is how it's used, how it's supposed to be used. Why is... I'm going to read what you have to say here. Comes to standing for it, I believe. I don't take it lightly when it comes to people messing with my beliefs. I do not take it lightly. Sure. I'm glad. I'm glad. But I don't feel sorry I can handle it. My parents won't homeschool me because we don't have the resources. But private school is really expensive, but I'm pretty tough. A lot of kids don't mess with me. It's not really about being tough. It's not really about taking things seriously. It's you're just surrounded by things that are not good constantly. Yeah, it's oh, what is this? Knowing that you're in a difficult place is half the battle. Knowing that you don't really want to stay there, because, like I said, it's not good. It's against Christian values. It's against a lot of things. There's a lot of things that are wrong with public school. They take a while to actually go through it all. Probably the main thing is that it's actually very expensive. So public school, I mean, it sounds like it's not expensive because because you aren't paying, but your parents are paying probably pretty heavily. Or at least where I grew up, it was very expensive. The taxes, you would have to pay for the public schools through your taxes. So it's not free, it's for people who think they can't afford it, for people who can't afford to pay both private school and their taxes for public school. It seems like private school is very expensive, but if you didn't have to pay your taxes for school, then you could pay that for a private school. I would highly recommend moving to a more affordable place in the country. There are places in the country that are, I'm assuming you're an American, there are places in the country that are way more affordable. That's actually what I did, is I moved away from that area because it was like, this is crazy, why am I paying so much money for public school, and public school is like garbage. That's the main thing, is that it's just forcing people to pay for something that's effectively evil. And then there's like all the ways that public school is evil is kind of a long list. But the biggest thing is it's just really expensive. True. I heard where I live, public school is free. That's probably not true. I mean, it's by definition not true. It might be free for you to attend, as in other words, it's not, they don't charge you a tuition. However, the people who live in that area, they have to pay taxes, and a big chunk of those taxes, usually property taxes, a large portion of the property taxes of the people that live nearby go towards the school. Now it's possible that you're in a very special area that like one person is paying all the taxes for that school, but very likely not. The person that told you that, they probably are just repeating a lie. They themselves are probably ignorant of it, but it's actually a lie. They like to tell people that public school is free, but someone has to pay for it. And the way it gets paid is usually it must be through taxes, and usually those taxes are levied from the property taxes. So my hometown where I grew up, taxes are like $1,000 a month for your house, and it's about $600 of it is for the school. So $600 a month per home in that area pays for the public school, which is insane. I mean, that's a tremendous amount of money. My rent where I'm at right now is it's like $758 is what I'm paying right now. So quite literally, you could pay rent in an apartment and live somewhere for that money, almost that much money. Yeah, it's really egregious. It's a lot of money, and it's a lie. To say that's free is a lie. And it's people repeat that lie mostly because they're ignorant. But it's free for you to attend, but your family has to pay for it. Your parents have to pay for it. People that you live with have to pay for it. You might not be paying for it, but they are, which in turn means you are paying for it. Because where are they going to get their money from if they're not charging you rent? And eventually they will charge you rent if they can't afford it, which is what my mom did. So unless you want to pay rent just to go to public school, highly recommend getting out of there. Highly recommend getting out of there. All right, so anyway, yeah, public schools. There are a lot of problems. A lot of problems with public schools. It's a really evil thing. And a lot of people think it's good, and it's really sad. But anyway, so let's go getting back to this problem. I seem to have missed something here. Somehow we missed the second element. I don't know how that happens. Let me see if we have. Oh, no. Okay. Yeah, so it looks like twice. We missed the second element. How does that happen? Oh, how do I figure out that? Yeah, I don't, Oops, no, not that one. Okay. Oh, that's interesting. We just missed this 5 altogether. It's so strange. In a Transformer stop motion, I'm making a video where one of the bots is playing the saxophone. Yeah. Stop motion is fun. Transformers are fun. I appreciate that. Not bad. The thing that's really weird about this is T is 100, T is 4. Why does T go from 100 to 4? Excuse me. Oh, I see. Okay. It's probably this routine here at the end. I see. Oh, that's why. Oh, okay, I see the problem. We don't need to do this here. That's actually the problem. Doing this twice. Yeah. There we go. Oh. Oh no. That was why I was so confused. Ah, there we go. Okay, I figured out why we weren't printing the last item before. So it wasn't the last item. We were skipping every other item. Okay, got it. I see. Sweet. Hey. All right. Alrighty. Now. Oh no. How do I exit? Oh, okay. Oh, I see. Okay, got it. There we go. By the way, the whole goal of this exercise was just so that I could print this list in a format that looks like this. So now to get back to the actual problem, dungeon game was what I was playing, and not playing, but working on. And I got stuck. Stop motion is super interesting. Actually, I need to go to bed soon. I have an interview tomorrow, which is probably gonna be really hard. I don't know how I'm gonna do tomorrow. I'm nervous to even attempt it. I really gotta go to bed soon. Let's see. Oh no, I forgot to. Oh, I gotta email not email. Message my recruiter, my job. Oh, I should have done that hours ago. I was so busy on my. Oh no. Uh-oh. I'll do that in the morning, I think. maybe I should do that now. I'll do that now. I'll just take a moment. Yeah, I've been trying to solve these problems. I've been so focused on it. Just give me a moment here. Oh man, I forgot. Okay. Whew. Okay. Yeah. Oh man. Oh, okay. So the whole purpose of that, the reason why I wanted to parse these inputs, excuse me, is, by the way, I think that's also one of the hard problems on this website is parsing a nested array. But what I want to do is find out what walking through this might look like and why we get the wrong answer. So, so we follow this. We follow this output here, so we can parse and pretty print. The idea is that each number is a health total. So you can move from the top to the bottom, and if it's a positive number, you gain health, and if it's a negative number, you lose that health. But I'm performing an algorithm on these numbers, and the idea is that as I'm processing each diagonal, I'm building two numbers at each point based off of the previous numbers, previous points. And I think somehow I'm getting the wrong numbers here. I don't know what's going on exactly. Can never figure out what is going on here, lol. I have to explain it. Yeah, it's kind of complicated. It's kind of complicated. So, all right. So this is the output that we have. All right, if we run this again. So initially, as we walk through, we have in the array, it's going to start on the right side. So we start with 748, 748. Didn't even eat. And then we say the next diagonal is here and here, 769, negative 62, 262. So to get to negative 626, you need, you would have to go through these two. So it becomes negative 31374. However, 769, you would gain some health, and you would still have negative 748. Okay. And then you can go to gain health here at 818 if you wanted to. That's the only way to go there. For 304, 306, this number would stay the same, this 31374. And then finally here through negative 343, you would only be able to go these three down. So 748, 636, 343. What's this? This is where you get, so the first, second, and the third. Third has three numbers, right? 748, 748, and then 1717. Okay. Now, the tricky thing is, from here, we're going to process every diagonal, right? So we're going to process these three diagonals, and then after that, it's going to be this diagonal. It's going to be sort of, each row has another diagonal it's going to move, progress down from. Now, part of the problem is we expect the answer to be, we should get 17118 at the end. So what that means is that the best path we could take would have to go through this point here. That's what we're trying to argue. And we're trying to show that any of these other points that you would go through would not give you the best answer. The best answer possible. Yeah. You can only move over to the right 4 times, and you can only move down, and you have to move all the way down some number of times. Oops. So what we're trying to do is 1718, 748, 748, 748. So what's interesting is that it's actually getting out of this spot by taking one of these 3 paths is optimal to get through this choke point here. So you can go this way, this one, this one, this one, this one, and then you're over here. And you can go this way also, and then you're over here. Although, so this one, this one, this one, this one, those 4 correspond to this here. Negative 4945, negative 205, 502, negative 51. Let's go all the way to the right, puts you at negative 51. This one is negative is 502, this one is negative 205, and this one is negative 945. Okay, and then you progress down from there. Till we get to the bottom 4. This one, this one, this one. Whoa, okay, so this is interesting. All of these, oh, okay. All of these other possibilities end up with really interesting numbers. So this one on the right very quickly becomes very negative, really fast. Look at that, very negative. These two in the middle are quite positive. But here's the issue, I think. This negative 1717 should never, never update itself to 748. That should be impossible. And the reason is, if you want to get to this point, anything from this point on, it'll cost you 1717. So I don't know what happened there. I don't know how we, this should always be the minimum value of what's there, what's already at that point. So in this case, 4 is this min f, sort of minimizing function. We should go through 4 iterations at most. Actually, yeah, so row starts off at 1, 1, 2, and 3. You should see 1, 2, 3. That's interesting. And then what's the next iteration from there? So we have 0, 1, 2, 3. So actually there should be 4, so this is not quite correct, I think. What happens if we set this to 1 and 0 here? I don't know. Okay, no, that is what we expect to happen. Yeah, that's what we expect. Yeah, it's fine. Okay. So that means is that we process, this starts initially, we do 1, 2, 3, right? Yeah. We don't print after the result though. Print before the result. We could add one more at the end here. Not sure if that matters much. Now the problem is that we have to select a tuple to update to or from. At each of these iterations, oh, I did this wrong. no! Oh no! Oh, that could have been so bad. Headset falling off of my head because I can't see. I have to keep moving around and I keep poking on the what is it, the charger, the wire that I've connected here. That could have been so bad. Wow. Oh, that could have been really bad. Yeah, so what's interesting is, oh no, oh, but we did lose our test case. That's okay, I have it saved. I have it saved in the spot, which is good. Okay. Phew. We're okay. We are okay. All right. So the issue is this point here. Should never go to -748. That bottom part of the diagonal. Excuse me. Because the only options that you have are from. So the question is it this loop or this loop that happened in, where it updated? Let's put a point here. Okay. Also, wow, it took us 6 hours, man. Whew. Whew. What a difficult problem. Oh, I did this wrong too. Also, my neck is aching. All right. Yes, so this is what it looks like before, but after the first routine here, we get some totally different numbers, which is wrong. So row equals minf, and we say row is less than the number of rows, add a row, and we're going to say select 0D RC, overwrite previous with temp. So select 0DRC looks like what? Okay. D starts off at 0. C is 0. Alright. I'm going to go up, walk up the diagonal. Sure. R starts off with this row. Sure. So if D is less than this position, which is 0, which will never be true, so you're never going to perform this. D is greater than or equal to 0, which it will always be, and D plus 1 is off the edge, then you're going to select the value you already have there. Otherwise, you're going to select between, if you have 0 and 1. So now here's the tricky part. You'll never be able to select. So 0 is directly to the left. So I actually think the array, or the diagonal, how it's set up, it's supposed to be the previous diagonal, same position, is actually right above it. So it's actually -1 and D, not D plus 1. That's what we're missing. That's why everything's wrong. I did have the right idea before, I was just not doing this correctly. So this should be position, and this should be -1. So it's D -1 and D. Yeah. Above and to the left, right. D is directly above, and to the left is D -1. So you have D -1. So as long as D -1 is less than the position, the lowest point, then we can't use it. If we're greater than equal to that point, we can. And then if these are both in bounds, then we can use either of these. And it's going to be D -1 and D. Okay, let's try something like this. I could pop my neck. Yeah, that's what I've been doing. That's what you see me doing here. I don't always pop my neck, but yeah, I can do that. I'm at the computer so often that that's the case. Oh, and this is D, and this is D -1. That's interesting. I'll come back to that in a moment. Oh, this is wrong. Oh, no. No, that's right. Oh. So if the check is for the first one, yeah, I keep messing that up. That's why we're getting these errors. But so now, oh, that's interesting. few things. I think this is supposed to start off at 0 now. Something like this, I'm not sure entirely. Kapopmanek, I just got 500 subs. Oh, you did? Okay. Great. Very good. I think. So this is very much the wrong answer now. Okay. Let's try to walk through some of these answers and see. What is going on now? So -748, -626, and -769. So it should be the previous oh. I see the problem. Ah, this is so confusing. That's why. I see. Oh man. Okay. I should keep D0 on the bottom left. I've confused myself multiple times doing this. Okay, I see. So actually, that's why it's so confusing. Okay. So let's put D, we'll start off at 0. Right. And we don't actually need a position, believe it or not. Don't even need that. This will correctly go off the edge in the top right. Oh man. So this is just confusing. This is just confusing. So this is the initial state, 1 iteration, 2 iterations, 3 iterations, and then the 4th iteration is here. So 1, 2, 3, 4. Okay. And that looks right. 748, 1374, 1717. And this one all the way over here is like roughly, is actually positive with the 748. And the third one. And this one is incorrect though. Oh, we do have to limit above what it can, oh I see. Do have to limit above what it can check on. I see the problem. That's what we used for the position. We could just say like AB. It's probably better. Lower, upper, something like that. It's a little bit easier, a little more flexible to do it this way. Okay, so for these cases, all of the lowers and uppers are just going to be 0 and min f. But on the first iteration, yeah, the upper bound has to be respected. So you don't want to use the zeros there. So the upper bound that we modify is, we'll say upper. We'll say it's is the upper bound inclusive? No, that's it's not inclusive. Really, it's going to be the D+1, pretty much. Yeah. Not D+1, it's it really would be like row +1, I think. So for the first row, you don't go to the one diagonal 1. Second row, you can look at diagonal 0, and you can look at diagonal 1. No, you can't look at diagonal 1. Yeah, for the second diagonal, you can only go to 0. Can't go to -1 or 1. Third diagonal, 3 elements, you can go to 0, 1, but you can't go to 2. Yeah. something like this. Something like this. What job are you wanting to get? I'm looking to work as a software developer. There are a few different companies I've been looking at to work as a programmer. Oh, I'm losing my marbles here. I'm losing my mind. Why is this not working? Really don't need this many. Really don't need this many lines to realize this is wrong. We can go to like 10 rows or something. Like this should be enough. Don't tell me it's correct. If it's correct, I'll be annoyed. Okay. Okay. Alright, that's a little bit better. So, we could probably get rid of more also. Okay. This is better. Alright. This is just wrong. Wrong. So, what's going on? How is this working? So we're saying we have a diagonal, and we're going to just keep iterating this diagonal all the way down. Let's actually use this case. Let's use TMP2. Okay. So what's supposed to happen is we're supposed to set up here initially, and then these two diagonals are calculated from the previous diagonal. This one takes a look upwards, and this one takes a look to the left. So this would be d minus 1 for this point, and for this point it would be d, right? D would be right above. And then we look these three, and then these four. Each of these get calculated from the previous values, positions. And then it's supposed to perform that iteration all the way down until you get to the columns. And then for each column, you're supposed to compute these in a similar way. And you just don't compute as many. And then finally, what you have at the end in D0 is what we return. I got to hold the snake? Did you? Hey, very nice. How did that happen? How did that occur? So that's the idea, but the problem is that this is not working. This is not working. This is not working. So, I guess for the first part, what numbers do we expect? pull out our handy dandy calculator, especially because it's hard for me to even read these numbers. My eyesight is so poor. So we have negative 748. Minus 626. Minus 343. Minus 772, or plus 772. Okay. And there's like 1717. So we would expect, so this is wrong. This is incorrect. Why is this incorrect? Because we expect 1717 to be on the left side here. For some reason we started with 626 and 769 is on the right side. I don't know where that came from. Oh. Really don't need these anymore, I think. Oh, I see. So actually, maybe this matters. This is a tricky thing here. This might make a difference, I don't know. This may not matter here. So initially it's 748, 748, but after the first iteration, oh, no kidding. Huh. Now how did that happen? Well, that's obviously wrong. These two. Okay. Row is 0. Greater than or equal to 0. Upper is 1. So this should be, this should just be D, right? D minus 1 is not a possibility. So initially, if you have 0, 0, then negative 1 is not greater than or equal to 0. 0, so this is false, this is false. Actually, this is true. Oh boy, I am so confused. This is true. And 0 is less than 0 is false, so this won't be true. This is false, this is false. So T should be a null pointer, so nothing should happen to the first diagonal. equals 0, row 0. Then we would decrement R. Overwrite previous with temp. Oh, that's why. Ah, I see. I was gonna say, I was like, how come they shouldn't have done what I thought it was gonna do? What kind of music you into? I was actually curious about how you ended up holding a snake, but I like I've been listening to a lot of hymns lately. If you have like here's one, something like this. That's good. Not a lot of hymns. I've been listening, not really too much music recently. Haven't been listening to too much music recently. Oh, there we go. We finally got the answer we were supposed to get last time. But now it's too much. Finally got what we were supposed to get last time. But now we're supposed to get 749, not that large number. Oh man. Oh boy. Okay. Huh. So. I don't know why this is so hard. Conceptually, this is kind of simple. My mom sells snakes. Oh, when did she start doing that? Does she always do that? What's the final state that we have? So actually, towards the end here, we should be able to update this number, this diagonal. I think the selection might be off, so we're supposed to pick. So confused. Yeah, the upper bound is just min f on the rows and the columns. Yeah, that should be fine. Okay. Oh, that's why. Okay. That's interesting. So this gets kind of weird. You have to actually start changing where D starts here. D actually starts at the column now. That's super weird. There we go. Dude, this problem's way too hard. This is way too hard. Drive me absolutely bonkers. Oh boy. Okay, let's try one more time. Signed them 1 year ago. Wow. And how does she like doing that? That's a very unusual thing to be doing. Kind of an atypical thing. Just take a deep breath here. Why is this taking so long to load now? I don't remember this taking so long before. Does she breed them too, or does she buy them and then resell them? I'm assuming she breeds them, so I guess she bought some eggs and then grows the eggs, hatches the eggs, and then sells them, and then maybe keeps some to get more eggs, something like that. Oh wow, this is taking a while. It's going slow. How are we doing on wow, we're almost 7 hours in now. She breeds them too? Gotcha. Snakes and lizards can be really expensive and people buy them. Oh no, we get a runtime error. Oh. No. Which one of these gives me a runtime error is the question. Alrighty. Well, we don't need that many test cases out the gate. Oh brother, we're like, I am struggling with this one. What a struggle. It's temp.py is the one that I was using. Okay. So let's do like 5 test cases. Let's say TT1. Oops. Yeah, all right, let's try that. 5 test cases. Can be really expensive and people buy them. Okay, interesting. So I guess people really like to, yeah, okay, fair enough, fair enough. Fair enough. Alright, so now the question is, which of these 5 does this error occur? Upon which of these 5? Probably just need one of these, realistically. question is why? This is, oh, okay. So we don't have that problem, then if we don't have that overflow, it looks like we're correct. Don't know how we got an overflow. Ah, there we go. Okay. So this one causes an overflow. Now, I wonder why. Okay. So I think in this case, the number of columns exceeds the number of rows. I think that's what's going on here. So before, if we had too many rows, that was something we could do, but if we have too many columns now, what do we do? Yeah. So before we had too many rows, now we have too many columns. So we're still going to be bounded by the number of the smaller of the two, which is going to be the number of rows. And oh, I see. Okay. So if we're going number of columns down, then the algorithm that I wrote before makes sense. But if we're going rows from left to right, then actually we'd want to go down and then, okay. Down and keep going to the right, or down and keep going down. And once we get to the right, we want to go down again. So down, right, down, or just straight down all the way through. Yeah, both of these should work fine. But the question is, why doesn't it work? What is the issue? Oh. I guess this upper bound. Oh, that's why. Oh, I see the issue. This is wait, what? Where does the runtime error occur? Okay. So much debugging. So much debugging. 10, 20, 30. So it's actually the last one here. Column is 1. Last row. Column, number of columns. Right, so at this point, we don't enter this loop. We would just go to the right. Oh, column doesn't equal 1 though. Oh yes, it does. That's correct. Column is 1. And we process all the columns. And oh, that's the problem. D is equal to the column. Oh, right. That makes sense. I see the issue. Oh, this is tricky. Oh. You don't start doing this part until the end. So we need to process the excess columns too. Oh, this is really tricky. So the part here is we want to process all the columns to the end. The number of columns we want to leave would be min f columns. So the number of columns minus min f columns. So if there are only min f columns, then this will be 0, and then we won't enter this loop. But if there's, let's say, min f plus 1 columns, one more column than rows, then you would process once that column. Right. This is correct. Yeah, row stays down there, column goes there, that's fine. And you process as normal. But D doesn't go to column, D goes to 0 here. And then now, process remaining columns. Looks something like this. So we made it to check 20. It's making my brain hurt, man. Got any pets? My mom has 2 huskies, Siberian huskies. She takes care of 2 huskies. That she does. Ah, this doesn't start with a 1. This goes to well, really, wherever this stops is where we would begin the next one. Something like this. I don't actually know where this runtime error is coming from. Apparently it's processing here is the issue. Why? Why is it even causing an error, by the way? That's my question. I don't even know why there's an error at all. It's the first iteration just immediately bugged. Why? What do you mean? Huh? (26). So minf drc 20. First iteration, first call. Immediately crashes. Why? Why? What is C and what is R? RCD. We know minf is 4. Well, I don't know. Oops. Okay, let's see what happens here. (1631) D is 31. It would also be helpful to know what the rows and the columns are. So I guess I'm learning we need more than just one loop, three loops. So there's 48 columns, 17 rows. C breaks down at the first iteration for C. D starts off at 31. Why is D at 31? Oh, here's where, yeah, that's the problem. D is just crazy. The idea here is we're eliminating D, so we pick D minus 1, and this is too large. So this is true, and this is also true. It's too large for the one on the right, but it's large enough for the one on the left. Oh, I see. Why is D at column? Oh. This should be min F. And this is, we'll just call it offset. I think I see the problem. I mean, you could do this too. That works also. That's why. That's the issue. Yeah. I think that's got something to do with it. Oh, still causing issues. Okay. Well, there's 17 rows, right? So we should also print the offset here. In my mind, this is so clean and simple, but actually coding it is like crazy. Why is it so difficult? Why is it so hard? I don't know. I think I need more practice doing stuff with things like this. Oh, the offset should be changing each time. No, it's fine. The first, no, it's fine. Excuse me. The offset initially would be, yeah, it starts at the offset here. I think it's supposed to be min F minus 1 also, but still, so we get all the way down to R is 0, C is 47, D is 17, the 47th column. And D is 17. And where does the error occur? Sometimes it'll tell you where it is in the program here. Can we try again? Where is this runtime error? Sometimes it tells you, sometimes it doesn't. Yeah, I could put a breakpoint or something. Nope, no breakpoints. Tank video. What's a tank video? What is that? Alright, so if we give these inputs here, R, C, and D. Also, I shouldn't be getting any runtime errors here. This is bizarre. I guess it has to do with the lower bounds and the upper bounds. But yeah, the upper bound should be min f. Lower bound should be 0. Yeah, it's confusing. I think the way I've formulated this is really confusing. Like the selection kind of routine. I think it's probably just really confusing, but also like walking through the test cases themselves, looping through the test cases is also really awkward. Using multiple loops for that, but anyway, so somehow this is incorrect. This offset. D. I think this is supposed to start off at column +1. Yeah, I think that's why it's not actually minus min f. It's minus min f +1. So min f leaves min f columns. We actually only want to leave min f -1 columns. There we go. That's why. Okay, I see the issue. All right, let's remove some debug code. The link won't work, but if you want to see it to my channel, yeah, I appreciate that. I'm gonna. Oh, I see. In other words, you tried to post a video. Give me the name of the video. How about that? Give me the title. I think we finally got it. I don't want to speak too soon here. We may have gotten it. May have finally figured it out here. I'm going to overstep my bounds here, or overstate here. Alright, let's do like 10. Alright, let's go for it. We'll do 100 next. Yeah, you can post the title of the video in the chat, and then I can look it up that way. Oh, I think we finally got it. I think we finally got it, man. I think we did it. That took forever. Oh, man. And here I am thinking I could solve these in 5 minutes each. uses 100 test cases now. causes my computer to lag. It's just so much processing. Oh boy. Oh. Oh. Oh man. Amazing. Ah. Come on, man. Which one is wrong? What? Is my algorithm wrong? Alright, this one says 466. Ah, I'd be so sad if my algorithm's wrong. 851 and 1. It's a 466 in there. Oh, okay. Expected 1, output 466. Alright, so I gotta search for 466 now. Okay. We're gonna find that number. 466, huh? $35, okay. So we can take our head 35 TT1 and tail that. Alright, this is the test case that failed. There she blows. There she blows. Get rid of this now. Okay. Let's see if let me get that to fail again. Industrial Insanity M1A2 Abrams tank. Huh. That's an interesting name. So expected 466. Expected 1, we got 466. Okay. If we pretty print this, what does this look like? Okay. So this is quite a few more columns than rows. One, 2, 3, 4, 5, 6, 7. It's only 7 rows and many, many, many columns. Okay. And this doesn't give us what we want. Is that because we skip a row or skip something here? Oh, so much work, dude. It's brutal. Trying to figure out where did I go wrong? Oh no. Ah. Whoa. What? Okay. Turning on the debug code. Alrighty. So there's only 7. So initially have all these negative numbers. And it looks like we can go all the way down here in this path. 271 all the way to the right. And boom, gets knocked right off here. So interesting. So somehow this occurs and we get 465 instead of 330, 236. Now how does that happen? This definitely wasn't supposed to occur here. This looks like the transition from see if we can find that point where that occurred. 465, 236. Somewhere in one of these rows, somewhere from left to right. Well, we could print the column that occurs on. I think that occurs not here, but here. Oh no. First thing, second thing, third and fourth. I think it occurs somewhere here. Something like this. Something like this. Okay. 465. So that's column 53 to 54. We just boom, drops down. Now what's interesting is all these other ones are way high. Wait a minute, we're missing something here. Initial rows, excess rows. There aren't any excess rows, so it's just the initial rows. This does look interesting though. Hold on, let's try this out. I don't want to get copyright infringement or anything. Oh, there you go. Oh wow. That's fun. Oh, that's a fun time. Using the Lego, I guess not Lego, but like a toy tank. That is fun. So 314, 314. Then and the next iteration is 529, so it drops a bunch. 215, and then 864 and 314, right? Yeah. Oh, that's interesting. Oh, I'm actually calculating this wrong. This 864. Oh, no, that's okay. No, that's okay. That's okay. Yeah, you would decrement 864 in order to update. Yeah, 314 is the lowest that I had to go. No, that's correct. That's fine. That's fine. Then 9090, 864. Oh, I see. You could do 774, or you can subtract 593. Huh. Where's the point where this switches over? See, the 729 on the left side is pretty rough. You know, the 729 is better if you wanted to go here. So in the first row, you get to this 271, and that's the best you can do. You have 1,000 health there. It's interesting though, you can make it through all of these. $12,000, $15,000, $2,000, $13,000. Yeah, all of these, it becomes optimal to go from the beginning. Whoa. You've got 3,000 health to work with over here on this side. And boom, you get knocked down. And everywhere else there's positive health though. Oh man. It's remote control. Oh wow, whoa. That's a pretty fancy toy. That's a fancy toy. Whoa. All of these have so much health, except this one spot. It's the only one. Oh man, that's disappointing. Basically, if you could get through the first few iterations with more health, but nope, you need negative 729 to get through this way. And then 90, there's just too many negative numbers in the beginning. 90, if you want to go down, so that's from 1 to this position from negative 774. If you go to the right, it goes down more. If you go down, if you want to go to 868, I think that's where this gets nailed. 868, yeah. Oh, I think. No, that's kind of weird. Is this calculating this correctly? Thinking about getting the Tiger tank, it's $279. Oh, brother, save your money. Save your money. $279. Whoa. I would say save your money and invest it. Save it, save it, save it. If I could have been making money when I was in high school and saving it, oh boy. Oh boy, I'd be retired now. I'd be retired now. Oh, this is killing me. How do I figure out what's wrong here? Which part of the algorithm is wrong? So in this case, we're just getting the wrong answer. We should be healthy all the way through. That's the problem, but we're not for some reason. And why wouldn't we be healthy all the way through? Well, at every possible path, we lose too much health. Is that true? Let me paste this into Notepad and not word wrap and see if we can find a way Oh, I see. There we go. So we can go here, here, and probably better to go here than here. So what are those numbers? See if we can find the path by hand. 314 plus 550 plus or minus 593 plus 388. Now we'll go down to 145. Let's go to minus 58. And then we're going to add 350. Right? And then we can go across 638. And then we're going to add 845. Add 564. Minus 37. $235. Oh, look at this. We can go 732. 729. And then 8950. And then 45. And then we can go all the way to the right here. I think from here we're in good shape. Yeah. We have to test each point, but this one should be fine. 4521. been saving a lot. I collect a lot of military stuff. Oh, I see. Fair enough. Sure. Sure. That's good. That's good. That's good. Oh, no. So now, probably from here we would be able to get through. Now, for some reason, we're not able to get through. What is that doing? Oh yeah, notepad. So we get down to this fourth one. Now for some reason it says we need 271, but we have 1,000. I don't think that's correct. Because we have a lot of options from the beginning here. So if we wanted to get to this fourth spot, so this is the second position. So the deal is we would check here, check here. We have some kind of a large number here. I was saying we would go here, right? Then here, so it's a relatively large number there. Then this number we can take from here instead of from here, right? Take the better of the two, the left and the top one. And what we want is, I think this is where my heuristic fails. At exactly this point, instead of taking the larger health, we took the lower, instead of taking the larger health at this point, we took the lower, I guess, amount required, if that makes sense. So that, I think is actually an algorithmic problem, and I'm very sad having thought about that now. The issue is this piece. So A and B, J and K. So it depends if A and B are negative or not. If B and K are negative, if they're negative, then we want to take the smaller of the two. So if we're healthy, we want to always optimize for health. If we've hit a point where we need a certain amount of health, then we want to not optimize for that amount. So that's kind of what I'm doing here. Now I think that's the error. I think that's the problem, is that it's not as simple as I'd like it to be. What we can do is we can run this routine once just to get the optimal health until we get to the end. Right, see, that's interesting. What I think we ought to do is the following. I think we should have two arrays. One array just gets the optimal health, and another array takes the so this takes the optimal health of all the paths, and another array will take the for each diagonal position, give you the like at each iteration the smallest number. So it'll minimize on every diagonal the smallest number that was seen at that spot. And the idea would be that sorry, I'm just thinking. Oh, I think my whole algorithm is wrong. After all of that, I think it's wrong. Okay, see ya. I'm going to bed. All right, take care on industrial insanity. Have a good rest of your night. I appreciate you coming by and saying hello. Oh, how do I, oh. You too. Yeah, thank you. Thank you. Oh, what great difficulty and what great struggle. I'm dying here, man. I'm dying. I have to go to bed. I have an interview in the morning. Oh. So the heuristic is wrong. I think that's the problem. Part of the issue here is I think I'm just worn out after this. So the algorithm itself, well, you would want to take the paths that give you the most health at all times, the most health. So and then what you want to do is also update. So you can update O(n) squared memory with what the lowest, I think you always want to optimize for the highest health. Always. And then you also keep track at each point of the lowest health that was seen with the highest health total. I don't think that works. Because yeah, we went over that before. Actually, in the example they had, we were saying that if you try to just optimize for the highest health, right? So you have -5 here, and then here the highest health is -2, and then this is actually, yeah, never mind. Actually, that's fine. That will give you the right answer. That will give you the highest health all the way through. Yeah. You're not trying to optimize the highest health. You're trying to optimize for the lowest point. Do you always want to take the path that gives you the highest health at the end? No, you don't want the path that gives you the highest health at the end. You don't even want that. Do you always want to take the path that maximizes your health? I think so, and the reason why you want to maximize your health is so that, now here's an interesting question. Does the path that gives you the highest health at all times, so sort of the optimal health, at the end, does that also give you the lowest required health for the journey? And I think that's probably true. What can happen though is you could have a path where you take a tremendous amount of damage and your health drops really low, but then after that you can gain a ton of health back, but you can only gain that huge amount of health by going through that area. Yeah, that's interesting. And you could also avoid that area too. Well, actually, our dynamic program is going to try every path. So yeah, you do just want to optimize the health at every point. Yeah, I think it is actually really simple. I think you don't use this heuristic that I have here, because I think it gets you into trouble. I think you just optimize at every point, and then just take the minimum you've seen so far. Yeah, I take back what I did before about this heuristic. It is just going to be the best, the optimal health every time. So that's this one. So if it's, so we're gonna comment this out. So if A is greater than J, or if they're equal. So if they're equal, we're going to optimize for the larger health, I guess, leftover requirement, I suppose. But otherwise, we go for A and J. Yeah. How about this? Wrong answer, still wrong. No! No! Output is 730. So, with our heuristic, oh. Our heuristic, we actually do better. So this is not exhaustive, is the problem. I don't think you can do this in cubic time, unfortunately. Yeah, it seems that the algorithm itself is wrong. After spending 7.5 hours, probably because the algorithm was wrong to begin with, that might be why. I had thought that you could do this in quadratic time, but it seems you have to do this in cubic time. I mean, cubic time is not too bad for this. But it's got to be, I think, at least cubic. Yeah, I think so. And the reason I think it's at least cubic is, you're trying to optimize for two different things at the same time. Yeah, which one is worth more, the total health or the health that is like the lower health, I guess. What if you did the other way? What if you just always optimized for the other side? Right, so we could say, how about that one? How about, yeah, always optimizing for this one. How's the job market now? How's it going, Mayuchi FR? I'm sorry, I said it wrong. Oh, wait, we don't really need to do this, do we? Sorry, I should. Mayuchi FR, how's the job market now? Howdy. It's okay. There are there's so many jobs out there. But I don't know, I've been struggling through LeetCode problems and I'm trying to solve all of them, but as you can see, I've spent 8 hours now on one problem. So if that's the rate, let's see if I could do 8 hours by how many problems? I have like 1,000 more to do. 8,000 hours, we do 40 hours a week. 200 weeks, it's gonna take me a few years. Oh man. You're gonna be a pro though. I don't know, man. I think I'm gonna just struggle and suffer. I don't know. I thought I already was at that point where I could just kind of bang these problems out really quickly, but I think I just struggle from time to time. Like I don't even know. I think the issue is I don't, there's a lot of problems, but like this particular problem, I think the issue is that like sometimes I try to think of an algorithm that's either impossible or incorrect. Either I don't understand the problem completely. It's usually what it is. I usually don't fully understand the problem that I'm working with, and so I try to do something that's impossible, and I'm spending like 3 or 4 days trying to do something that's just literally impossible. And I lose so much time. I lose my mind. I think that's what's happening here. I think it's impossible to do this in quadratic time, possibly. And so here I am optimizing an incorrect solution, and so I'm just constantly getting the wrong answer over and over and over again because it's not correct. There's no way to do it in quadratic time, so it's just always going to be wrong. Even if you spend 7 hours, you're still going to be wrong. Or I'm still going to be wrong. So I think that's the problem I'm running into, is that I'm just not I'm not doing it right, man. Just not doing it right. So here we optimize for the second part. We optimize for the remaining health, but still somehow we don't get the right path that gets us to the end. I don't know. I don't know what the right algorithm is then. Yeah, we're using something of a heuristic. It's not correct to take the path that always gives you the highest health. Well, that might not be true. That might not be. Yeah, I don't know. I'm so confused now because maybe you're. No, it's not true. No. You always want to take the path that minimizes. It's not that you minimize the. You want the path that after the entire path, you've minimized the. After the entire path, you've minimized the amount of. After the entire path, you've minimized the amount of health required to survive that path. That's what you're trying to minimize. You're not trying to minimize at every step, though. That's actually incorrect. Unless you're looking for the top highest paying job. For a web dev job, you probably won't need it. No, I probably won't. Well, I wanted to work at Google for the longest time. And that was the plan. And I was going to interview for an L4 position. I just wanted to be prepared. And then someone explained, like, well, if you do all these problems, you'll be prepared. And I was like, okay, well, I'll do that. And I am at the point where, like, some of them I can do in, like, 5 to 10 minutes. But, excuse me, but, like, I have to be kind of really on it somehow. Like, I have to somehow be able to figure it out. So I think we can't do this in quadratic time. I think it's a lost cause is what I'm trying to do. So let me try, yeah, I think I probably would have had it by now if this was correct. So I think what I should try to do is go for a recursive memoized solution and then just get the correct answer, probably cubic time, and then try to memoize that and with a then try to optimize that with a DP solution, dynamic programming solution. So in quadratic time and cubic time, what was it saying? Quadratic time, cubic time, DP solution. Yeah, so I'm pretty sure if I get a cubic memoized solution, like that'll be sufficient. That'll be enough memory. It might be too much memory. That's a lot of memory. But I think that'll work. But the question then is like, okay, well, how would I solve that? Right, so at every point you have two choices you could make. You want to optimize for, it's not just optimizing for, you want the most health that you can get, but you also don't want to take a path that puts you in a negative value for like the minimum required health. Yeah, it's weird how it works. Like you. Because if you take a path that gives you less health overall, then you may be forced into a position where you'll take a very large hit, and then now you've lost all of that optimizing on the lowest health, or like the health requirement. Some reason though, this seems to work reasonably well if I optimize for just like the required health on that particular path. Like I said, I'm wondering there actually aren't too many decisions you can make. Because at each step you only have two choices you can make, right? And then how do you make that choice? I think that's part of the problem, is that, yeah, you could look at it as maybe more than one choice. So I think the way to look at it would be maybe all of the choices for a particular row. Maybe you want to do row by row, or sorry, column by column. Let's say like column by column. So you can go all the way down to the bottom of the column before you move to the right. No, that isn't necessarily what we want either. I mean, that's encompassed in what I just did. I don't. Thinking that there's only two choices, I think, is wrong. Let's start with that. Yeah, because you're actually choosing from a whole set of paths, which is a huge set of paths. It's an enormous set. That's an exponential number of paths. Yeah, you could do more than one look ahead. That's the thing. Is you can go for like multiple levels of look ahead, quote unquote. But why do that? But why? I think this is similar. No, that doesn't work. No, I think it's too big to do this in quartic time. I can't even think of a cubic. I don't know why a quadratic wouldn't work. I don't know, man. I'm stuck. Stuck on the question. At least you're motivated. That's great, man. I hope you do it. I'm looking for an entry job. I hope we can make it. Yeah, go for it. Yeah, sure. I don't know what to say about entry-level jobs. I have no idea. I would say, as far as like the technical portion, they want to know. Well, entry-level jobs are. I'm actually not sure what to say about that, but I could say certainly for like pretty much any job you go for, like they really heavily test data structures and algorithms, like this stuff, LeetCode questions. But if you just want something entry level, like probably, I don't know what the standards would be. I guess you just have to try a bunch of different companies and see what they test you for, and you'll get a sense of what they're looking for. I actually wouldn't even know what to say about entry level jobs. I don't even know. Should I focus more on Python or JavaScript in your opinion? That's a good question. Python's pretty good. They're both really good. JavaScript's really good for front end. Python though is extremely good for both like the data structures and algorithms questions, and also just like coding for like web development. I would say they're both pretty good. Probably, usually Python's more back end, JavaScript's more front end. So I guess it depends on what you want to do. Python's super easy to learn though. Python, like literally like the docs for Python are like very easy to navigate, and there's like not that much to learn, quite frankly. Yeah, I guess like learning like Django is pretty good. I still on my list of things to get to. What's the other one? React, Redux, Django, Angular. Like there's a bunch of front end frameworks that are worth learning. I learned to React. It's pretty good. Yeah, I'd say they're both pretty good. I guess it depends on which one you have less experience with. I'd probably focus on that. Keep them kind of even, the amount of time you spend on both of them. I'd say even. Thanks, man. I hope I can do those challenges one day. Yeah, these are fine. I mean, these are, they're not that hard, actually. You kind of just need someone to guide you through it, like how to do it. I say that while I'm still struggling on this one, but it's tricky. I don't know. There's like, it's taken me a really long time. I think if you get coaching from someone, then it's a lot more efficient. Like there's sort of techniques you can employ, but obviously there's some techniques that I still haven't fully grasped. Yeah, this has got to be, I got to think about this problem a little bit more. I definitely have the wrong idea. That's definitely it. I definitely just have the wrong idea, but I can't think of an obvious way to approach this. Let's see, we have, what is this test case? -2, -3, 3, -5, -10, 1, 10, 30, -5. All right, let me start with a brute force solution that I know is correct. Well, you can go through every path and when you're done, so at each path, at each step, you're gonna, at each step of your path, you're going to check to see how much the smallest amount on that path, what the smallest amount on that path was. And yeah, ultimately we're going to try to minimize that number, I think. But let's say we say check the smallest number on that path. And we can go through all the paths, right? And that would be expensive computationally. But there's a lot of different paths and potentially a lot of different numbers we end up with. And then we take the minimum of all those numbers. And if it's a negative number, then we negate it and add 1. If it's a positive number, then we just reduce that to 1. That's all well and good. Now, what's interesting is you can arrive at the same point in a path, and you could have 2 different numbers, though. Like you can arrive in multiple different ways, but you can have 2 different numbers. You can have a health, and then also, oh, did my pen run out of ink? No, I don't think so. You can arrive at this path in 2 different ways, or multiple different ways. Now here's the tricky part. How do you optimize for that point, right? Because you want as much health as you can, but you also want as much. So that's why this is not just a simple quadratic time dynamic programming solution, because you have more than just the health to optimize for. You have 2 variables to optimize for, which is the health and then the sort of required health. We'll call it RQ, right? H and RQ. Or H and RH. You have health and required health up to that point. Now, what's interesting is you don't necessarily want in your paths. So if we just went through every path, right, that would be way too expensive. So maybe we only want to go through some paths. So let's try to get this down to like a. No, we don't necessarily want to make it a cubic algorithm, but like, I mean, each path there are only 2 choices to pick from. How you get to each point. Trying to think here. Yeah, we can't memoize. because we don't know. Yeah, interesting question, because we don't want to. This is a really tricky problem. This is a really tricky problem. What exactly? So okay, so we got to get my mind out of thinking that we're going to do this in quadratic, anything remote related to quadratic, even though it's a matrix, even though it's a 2D array. That third variable for the required health means that we need to think about something else. What we could do is at each point we have all of the possible paths and all of the possible health and required health pairs. There we go, so we have a list, right? So at each point there's a list of these things, right? And that gives you all of the ways that you could have gotten to that point with this, with this list. All the ways you could have gotten to that point. All the different paths you could have gotten to that, all the paths you could have taken to get to that point, with the associated health and required health pairs, right? So we have all these pairs up to that point. You have a list of them. And that could be sort of somewhat memoized. Yeah, so in order to get the next list, you take the previous two paths and their lists, and you would say, basically combine these two lists, and you get a another list where you add the health and update the health and the required health for each of those values. And you can prune that list, I think. But not too much. So that's kind of interesting. I'm wondering, oh no, yeah, you could somewhat prune that list. You know what you could do? You could use an unordered, well, no. I was going to say there are some variables there that are just always better. So if you have more health and less required health, like that's just better than another selection. And you can optimize that out, I guess, prune that out. If we could maintain these lists at strictly linear sized lists, that would help a lot. That would be really good. And then we can do this in cubic time. But actually the number of ways you can get to a particular point, the number of paths is actually, there's a very, very high number of them, a very large number. Yeah, so those lists will be very large. Excuse me, actually, what would overtake the algorithm? Wouldn't be so much, the quadratic kind of memoization, but it would be the just copying all of the other values into the list. You can maybe condense these lists and say, well, actually, you can kind of hack this a little bit where, oh no, you can't, never mind. I take that back, you can't, never mind. Excuse me. Yeah, you can take, like, you can prune pairs where if you have a certain amount of health and a certain amount of required health, and then you have another pair that has greater health and a lowered required health, then you can eliminate the previous pair. Not sure if you should perform a round robin check. I'm trying to think, how can you compare these, right? Because you don't know what the value of the health and required health, what their values are with respect to each other, right? In order to, correctly eliminate some of these values. Yeah, I don't see too many other options here because you don't, like I said, you only have so many options, so many choices to make. I'm wondering if you could maybe make this cubic or quartic where somehow you optimize for both of these variables in your choices simultaneously. Excuse me. Maybe you do a similar thing like we did. There's another problem that was similar to this that we did where we used like a double look ahead. So instead of doing right and down, we did right and down and right down and down and down right. The idea was if we did that, then, well, was kind of special. Like there was another kind of an optimization there where we were just taking a simple sum over all those values. And the reason why we did that is that there was one path that would go down, and then there would be another path that would come back. So we were simulating both paths simultaneously. And yeah, basically it would be. Wait, why did that work? I'm trying to think. Wait a second. Why did I do that? Actually, I don't remember that. Remember now why that works for that problem. I don't remember now. The reason why a double look ahead works for that situation is because. Oh, no. Excuse me. Right. I see. No. No. There was two paths, so it wasn't a double look ahead. It was actually two different paths. One path going there and one path coming back. That's why. So it was actually computing two paths at the same time. And if you did that, then you can memoize over 4 variables. Right, you have two different indices, 2 pairs of indices. I don't know what the dynamic programming solution would look like, but the memoized version worked out okay. Yeah, that was a pretty interesting question. And yeah, so I forgot how I calculated it. I think the way that I calculated it was you would if the position that you're at in one path and the position you're at in the other path, if either of them there was like a number you would add, you would add the numbers at those 2 spots, and then you would add that to the maximum of the possible recursions that you could take from there, which obviously there were. Each path had 2 different directions you can go, so you had 4 of them. You had, it looked like, I think it's 16. It would be 16 different paths you can go, which is pretty interesting. You memorize all of that. No, actually, it's only 4 paths. Yeah, because each is 2. Yeah, it's 2 paths, and each path could take 2 different directions. So it was only 4 choices. Excuse me. It was only 4 choices. But the question here is, we're not doing 2 paths here. That's not what we're doing. I don't think so. 2 different simultaneous paths. No, this is something else, something different. Yeah, because we're not coming back. We're not making a cycle. we're just trying to get to the end, the bottom right. But there is one more variable here that's like I want to keep track of. This is super challenging. I don't know what the solution is. I don't even know if I have a memoized version of this. How can you do that? Let's see. So the brute force solution I have is just every path, and then the other possible solution that's slightly better is record all of the solutions up to all the possible paths up to a certain point. Yeah, so if I just consider like the bottom right corner of like the ending goal, and if we just consider like a section of size 4. And the problem is that to get the bottom right solution, you would need to know which path. You have a few things to check, right? It's in order to select the right path there, it's which one gives you, if you take damage at this point. So if you don't take damage at this point, at the ending of the goal, if you don't take damage at the goal, then you can just take whichever one has the smallest required or the largest required health, or the smallest required health, let's say, yeah, or smallest required health. If you don't take any damage, that's all you need. If you do take damage, though, then I think you want to optimize for both the required health and the health that's being brought to you up to that point. So if the damage would not, it depends on how much damage it is, how much health you have in each spot, right? If the damage compared to the health and required health of one of these selections would decrease the health so far that it actually changes the required health to a smaller number, then you have to consider that. That would actually reset both your health and your required health, right, to smaller numbers. You'd have to compare that to the other potential value, which is similar, right? There's a health and required health. You want to know what's the health and required health after you take the damage, and compare those two. And what you end up with is you want the lower required health of those two. Now that's a question. Is that true? The optimal required health up to that point would be, at least if you're looking at 4 blocks, since the health can't change, your initial health can't change. This is kind of a pure example, I guess, in that there's only one option for the rightmost selection, and there's only one option for the downmost selection. So if there's sort of like H1, H2, H3, and H4 from, left to right, top to bottom, red left to right, so H1 in the first, so the top left is H1, top right is H2, bottom left is H3, and bottom right is H4, have something like that, then we know the path right and down and the path down right are the only two to consider. The intermediate point would be H1 plus H2, and then the required health is depending on whether H2 is damage or not. Might be, we don't necessarily know what, we'll go at RH required health of 2, and obviously H1 has a required health of 1, H3 has required health of 3, and then H4 has required health of 4. So H2, so the path there is H1, H2, and then this required health 2, we'll explain in a second. And then H1 plus H3, and again, required health of 3. So what are the possible values for the required health of 2 and of 3? Well, H1 is less than 0, and H2 is less than 0, and then required health of 2 is equal to H1 plus H2 negated, right? And so there's 4 different options for H1 and H2. H1 could be greater than or equal to 0, and H2 could be less than 0, in which case the required health is the negation of H1 plus H2 again, right? It's I mean, it's the negation of that every time, I think. Yeah. So actually, it's just going to be the negation of. So if this is a negative number, that means the required health is 3. Yeah. Excuse me. Interesting. So, okay. I know the required health for 3 is the same deal. It's just the negation of H1 plus H3. Okay. Oh. Well, that means that, oh. Huh. No kidding. This is not as hard as I thought it was going to be. Is it? Wait, what? Huh. So actually calculating H4 is actually just the maximum of H1, H2, and yeah, it's just the maximum of H2 and H3. What? Yeah, because when you add H4, which is either damage or not damage, it just moves your required health in the opposite direction. Wow. Huh. That's interesting. This is really confusing, but I think all you've got to do is maximize the health. I don't know why. I don't know why this is so difficult. I think you just maximize the health at every point, and if you do that, that also minimizes the required health. Is that true? Yeah. All right, H4 and RH4. H4 is just H1 plus H3 plus H, or yeah. I'm mixing my variables here. That's really awkward. It's going to be, we'll call them like alpha 1 and alpha 2, alpha 3, and alpha 4. So alpha 4 is H4 plus the maximum of alpha 2 and alpha 3. And RH4 is what? Well, that's the scenario we were just describing, right? In order to maximize the health for alpha 4, you'd want H4 plus the maximum of the other two. And what's interesting is these RH3 is literally exactly negative alpha 3, and RH2 is negative alpha 2. Is that always the case? Actually, I don't think so. I don't think it's always the case. And what we were saying is that if we add, if H4 is damage, then what do we want to do? So if H4 is less than 0, let's see, well, if H4 is positive, then we just want to pick the smaller of, or actually we're gonna maximize negative alpha 2, negative alpha 3. Oh, excuse me, minimize. Yeah, the negation is the required health, so minimize negative alpha 2 and negative alpha 3, which is the negation of the minimum of or is the negation of the maximum of alpha 2, alpha 3. Alright, if we took the absolute value of these two numbers, or if we negated these two numbers, then we would want the one on the right of the number line. Yeah. So the negation of the maximum of these two, alpha 2, alpha 3. That's if H4 is positive, right? And then RH4 would then be the difference between H4 and these. But if H4 is negative, part of the problem is what RH4 would end up being if H4 is positive. So it would actually just be RH4 would just be whatever these two numbers are. Required health. And I think you just always add 1 to the required health, because you need to start with a 1. And the reason why it's just the maximum of these two numbers negated, well, if it's a negative number, you'd negate it and add 1. If it's a positive number, then you just add 1. Or no, excuse me. If it's a negative, if your required health is a negative number, that means that you get health. You have plenty of health on that path. Excuse me. So yeah, if you heal on that path, on that spot, then you would just take whatever your values that you found at those two positions are, and you just take that as it is. If those were the optimal like required health amounts, then you just take the optimal of those two optimals and you're done. But if you take damage, then the problem is that if those two values are the best you could do, now it depends on how much health you have with those two values, because if you have a lot more health and the value isn't optimal, you could be in a situation where taking damage will put you below the optimal for either of those positions or both of those positions. That's when things get really interesting. And in that case, you would actually want, in order to optimize that value, you would actually want your health to be very high at those points. So that you don't go as far down. And that is where the problems come in, because how are you supposed to know, like, in other words, getting the optimal solution at those other 2 points is no longer the goal in general. You need something else, like depending on how much damage there is. Granted, you're dealing the damage to both of these two, or both of these options. So the question is, do we need to think up a whole new algorithm to factor this in, or can we still use the two optimal amounts? We said alpha 1, alpha 2, right? So alpha 1, or alpha 2, alpha 3, and then RH2 and RH3. And then there's this H4, which is a negative number. Yeah, the question is, can we depending on the damage that's being done, if we suppose for a moment we only had these two choices, and we want to optimize RH4, which is going to be related to, so we say alpha 2 minus H4. We'll say H4. Let's just take the negation of H4, right? Call it a positive number for now, even though we're going to subtract this positive number. Excuse me. So alpha 2 minus H4 gets you to some number. Call it x sub 2. Same thing. Alpha 3 minus H4 gets you some x sub 3. Now, if x sub 2 this is a negative number potentially, so if we negate this, and we're saying the required health is a positive number, right? So required health 2 is a positive number, negate x2. If x2 is greater than RH2, or if x3 is greater than RH3, then the required health of 4 is going to be dependent on these values. So negative x2 could be greater than, so we take the maximum of negative x2 and RH2, and also the maximum of negative x3 RH3, and finally you're going to take the maximum of those results. So it's the maximum of negative x2, negative x3, RH2, RH3. That's got to be RH4 if you take damage. Interesting. Yeah. Excuse me. Now here's the question: if you heal and you don't take damage, you do want to take the lower of the values. Because that's what we're looking for, right? But it might be beneficial for future steps to optimize for the health at that point. And that's the tricky spot. I mean, that's the thing that we're getting stuck on, is Excuse me. If you take damage, you probably want to optimize for health. I mean, in every case, you want to try to optimize for maximum health. But there's also, you are ultimately trying to optimize for required health. So there is some tension here, choosing between maximizing your health and maximizing your required health. At some point, it's advantageous to maximize your health, and other points, it's advantageous to maximize your required health. And trying to figure out which ones are best is tricky, to say the least. So you could argue, maybe we can do a quartic solution here, where you could take each path, you could take each possible selection, you could take both selections, right, and optimize for the sequence that you picked. Optimize for the sequence where you picked the one that had the highest health, and then you could, the other one where you picked the highest required health at each step. So actually, the two choices are not between left and down and up. The choices are not between left and up. The choices are between the optimizing for the health and then optimizing for the required health. One of those being a left choice and one of those being an up choice. And those give you two options per node, I guess. That gets really confusing. Yeah, this does just give you a quartic memoized solution where you would say I'm actually not sure. No, I don't know if that's the case. You would I don't know, I guess you'd have, let's say you're like, there's some path you've taken so far, and you could say, okay, I can go to the right or I can go down from this path. Let me optimize for health, and let me optimize for required health. and perform those two different optimizations. And so now your path might take two different approaches. And then each of those paths, you then make the same choice again. But the decision to, so there's sort of four decisions to make. There's take a right and optimize for. So I guess this is like the same quartic question that we had before. I think it is. I'm gonna lay down for a few minutes. I think this is actually very similar to the previous problem that I was describing, where you're not taking two separate paths per se simultaneously. It's more like you're taking one path, right? And on that path, there's another path you could take. And that second path that you could take is an optimizing path. I don't know, man. This is too hard. This is a hard question. Let's try to do this top down first, and then we can think about DP later. You can only go to the right or go to the left. Top down. Okay. Excuse me. No, but you want to optimize for the health and also optimize for the required health. And in some cases, it's better to optimize the health. In other cases, it's better to optimize the required health. So we want to check all of those possibilities, right? Now, checking every possible path and the required health that we end up with after we evaluate that path, that's very ineffective in terms of cost efficiency, or it's extremely cost inefficient. Let's see, what can we do? I think I need to go to sleep and make this a part two again. Yeah, I'm falling asleep over here. Let's see, cost inefficient with respect to the path. Hmm. There's this part of me that's wondering if it's as simple as just calculating the optimal health at every point. And then just finding a path where the minimum optimal health from that path to the bottom is smallest, or is actually maximized. Or that's the maximum optimal health. The minimal, how do you express that? Such that the healths that are negative, the optimal healths that are negative, are maximized. Which is to say they're closest to zero as you can be, as you can get.
Alright, anyway, so make this part one, we'll come back to it later. Yeah. I couldn't think of the answer. Didn't get there. I'll try again later. Alright. Alright. So okay, oh, I didn't realize Major already left. I was gonna respond to him, but I don't know. I'm just gonna go. I'm like falling asleep here. Alright. Yeah, so that was over 9 hours of just thinking, I guess, or just trying to solve this problem. Alright, I don't know. There's something I'm missing, I think, with the problem. Let me go to sleep and then we can look at it later. So yeah, thanks again. Talk to you soon. We'll make this a part one and then return. Make this a part one. Alright, I'm gonna go. Thanks again. Take care.